So good morning. Welcome to the third day of LXMLS 2016. So today we have the great pleasure of having Noah Smith with us. So let me say a few words about him just before the more formal stuff, which you can actually look up by clicking his name on the program. But I'll mention a few things. So Noah and myself are the only two people who talked in all 16 editions of LXMLS. So we are both historical dinosaurs, although he's much, much younger than me. So it's great to have him once more to talk about sequence models. So Noah serves currently as the Vice Provost of AI, and he has an endowed chair at the University of Washington. He's also he's a professor in the Paul G. Allen School of Computer Science and Engineering, still at the University of Washington. And he's also the Senior Director of NLP Research at the Allen Institute for AI. Any other interesting, any important things I should mention? That's okay? Okay, thank you, Noah. Thank you. It's great having you once more. And the floor is yours.
Thanks. Can you hear me okay? All right, good morning. Thanks for getting up. I'm delighted to be back in Lisbon again for probably about the 20th time. Really, this is a fun lecture to give. If you want to know what a vice provost is, ask me during the coffee break. But when I took on that job about a year ago, I stopped teaching to make time for the administrative work. And so this lecture and the occasional guest lecture and like public talks are the only opportunity I get to teach now. But this is my absolute favorite topic. So I'm delighted to tell you a little bit about the history of language models. So basically the goal today is to talk about sequence models, language models up to, but not including the transformer. So if you already know all of this, then you can go to sleep. If the only thing you know about is the transformer, this will be sort of the journey of how we got there. And then I think tomorrow Andre is going to teach the transformer. But I think it's good to know the history. This lecture is going to try and give you the mathematical foundations so that you will be prepared for changes to come in the space of language models. I don't think the transformer will last forever. I think there will be other things that you'll have to learn about, but the fundamentals you'll hear in this lecture will help you be ready for that, and you'll be unsurprised. I'm not going to predict what those changes are, but I think you'll be unsurprised by the directions that follow after this lecture. I also like to point out that I think language models have become very important. I think pretty much everybody in the world needs to have a basic understanding of what they are. And so with some of my students, I wrote this tutorial called Language Models, A Guide for the Perplexed. You get the joke? If you don't get the joke, you'll get it by the end of this lecture. That came out on the first anniversary of ChatGPT's launch, so that was in 2023. So if you know somebody who should understand language models but doesn't have the same technical background that got you to LXMLS, this tutorial or the accompanying talk are materials that are intended for that wider audience. There's no math there. Okay, why learn about language models? A lot of these points, by the way, are points that I made well before language models became part of everyday life. So they seem kind of obvious now, but if you put on the perspective of I don't know, 2020 or 2015, when we had the Lisbon Machine Learning Summer School and we were talking about language models then, we knew they were going to be important. And one of the reasons that language models, one of the applications of language models that we talked about back then, before they became part of everyday life, was autocomplete. We've all had this experience. It's now very widespread. You're texting or you're writing an email, and the computer suggests the next word. And that is the heart of the language modeling task. What is the next word going to be, given the words that came so far? This also is, we now see people using chatbots all the time in kind of a conversational mode. You ask a question, it gives an answer, you ask for clarification. The interface with which we interact with most AI today looks exactly like the same interface we use to text with our friends and family. So thinking about dialogue, about conversation, that's another good motivation for thinking about why we might predict the next word. But there were a whole bunch of other applications that generated text before the language model moment that motivated the need for language models. Sorry, I keep moving. Is it? Okay. So these include things like transcribing speech into text, still a very widely used technology. Translation from one language to another. I used it this morning. Now it's built in. You just press a button in Gmail and it'll translate a Chinese email into English pretty well. Summarizing documents, captioning images. I think there's a beautiful problem that for a long time was understudied called optical character recognition. Take an old book that was printed hundreds of years ago and all we have is an image of the page. Can we digitize it? And many others like spelling and grammar correction. So basically, there's this whole class of problems where you have inputs, call them I, and you want to map them to a word sequence. And in most of these cases, there's a fairly well-defined target word sequence that you want to output. And so the task usually would break down into two parts. One part was you want to choose an output sequence that's faithful to the input. So that depends both on the output that you're generating and the input. There's like a good matching function here. But there was a second part, which was we want the output to be highly fluent, right? We want it to sound like natural language. This was the heart of Leon's talk last night when he talked about, he called language models fiction machines. I'm not sure he used the word fluency, but that's the word I use to talk about the idea that the language model helps us detect or generate text that has high fluency. It's believably language. So that was the job of the language model, and then you'd have another component for doing this part. There's another reason, I think, to study language modeling that is often forgotten about. I sort of had one foot in AI for my whole career, and the other foot is just like a deep interest in language. I did an undergrad degree in linguistics, and you know, I wouldn't say this is the mainstream view in linguistics, but I think a lot of people take this view that if you're theorizing about language and you have two theories, A and B, then one way to judge, an important way to judge whether theory A is better is whether it's less surprised by the data. If we have some way to measure the surprise that a theory experiences when you expose it to new data that wasn't used to build the theory, then maybe language models give us this notion of surprise. And in fact, that's exactly what they do. And so if you're trying to decide what is actually true about natural language or about some subset of natural language models might be useful there as well. Okay, in order to talk about language models, we have to start with probability. So we're going to do a very quick review of the basics of probability to get the terminology and the notation back into your head. I'm assuming you've probably seen most of this before. In this lecture, we're dealing with discrete probability spaces. So if you're a computer scientist like me, you can relax. If you're coming out of electrical engineering like Mario, then I guess you can relax as well, but you look calm, yeah. So we have random variables. These are going to be discrete random variables, and we usually write those with a capital letter. And we typically have statements, if we're going to be very, very explicit and spell everything out very carefully, we say random variable big X takes value little x that comes from this set script X of possible values that the random variable could take. And we give that probability that big X equals little x. We often use shorthand and just write this as P of little x, but whenever we have probabilities, you should be thinking in the back of your mind, there's a random variable here. Do I know what it is, and do I know what space it ranges over? And usually when we're doing machine learning in 2026, there's not just one random variable, there's many random variables, often at least two. And so we can have joint probabilities. So this is the joint distribution. And there's this comma really is implying an and. So this is the probability that big X takes the value little x, and big Y takes the value little y. Both of these have to be true to have the event be satisfied. And so we're talking about a smaller probability probably than either X takes the value X or Y takes the value Y. And then there's this related quantity that's really important, which is the conditional probability that X takes a value little x, given that Y takes a value Y. This is familiar? Nod and raise your hand if you're happy and this is all like, you've seen this before. Okay, good. And by definition, you can think of the conditional probability as a ratio between the joint and the marginal probability of the thing on the right-hand side. Okay, so some things that are always true, just following from the definition, you can always break a joint distribution down into a product of a marginal and then conditionals. And you can do that in either direction. So this is just true. There's no, like, you just get this for free. It follows from the definition. This is just how probability works. But then there are some things that are sometimes true. Like, it might be the case that the joint probability of the two events is equal to the product of the two different probabilities of the events happening separately. Can anyone say what the name of this property is when it holds? Independence. This is true if the two random variables are independent. Another point that I like to raise early on, we can talk about probabilities all day, but there are usually two kinds of probabilities that people sometimes conflate. One is the probability in reality, right? Like the true probability that that an event is gonna take a particular value. But more often, when we're doing machine learning and when we're doing AI and when we're building language models, we don't know the true probabilities at all. And we might even not 100% personally believe that they exist. It might not be so simple. I think this is part of what Leon was getting at last night when he said there is no real general distribution of language. Everybody has a different one because we all are exposed to different things in our lives and have probably different models in our heads. So the true probability distribution is kind of a useful fiction that we use when we prove theorems and when we talk about the properties of our models. What we're mostly dealing with day to day when we build things is estimated probability distributions. And so sometimes it's important to make that distinction. Okay, let's a couple more notational things before we move on. We are always, when we're building language models, going to be talking about a finite vocabulary. We use V for vocabulary. It's the set of symbols. They could be words, they could be characters, they could be something else kind of in between words and characters. We'll talk about this a little more later. But it's a finite set, and we always sort of start by assuming that we have this fixed vocabulary, and it has a fixed size, which we'll call big V. What we're interested in when we're doing language modeling is not this finite set by itself. It's the infinite set of sequences that you can build by chaining together choices of words from the vocabulary. So in language modeling, you want to think about a sequence of random variables. X1 is the first word in the sequence. X2 is the second word in the sequence, and so on. And this continues arbitrarily long, right? Books can be arbitrarily long. Conversations can be arbitrarily long. Lectures can be arbitrarily long. But they always have an end. For one reason or another, it will always come to an end. And so some xn, for some value of n, will eventually take this special stop sign value. And so we call that the end of sequence symbol. I like the stop sign because it's internationally recognized. Everybody understands it. So what we're really interested in when we build language models is the infinite set of sequences of symbols from V with a single stop at the end, which signals that the conversation or the book or the discourse or whatever has ended. There's always an end. So we're looking at the infinite set of finite sequences. Make sense? From now on, you have to end everything you say with stop. All right, so here's the language modeling problem. You're going to get some data, which is a big, long sequence in that set, VDagger. And maybe, it might be useful to consider this a collection of observations, each one in VDagger, but that will make my notation more complicated. So for today, we're just going to imagine that there's a single long sequence. My entire training corpus of trillions of tokens is x1 through xn. And my job in building a language model is essentially to construct a function that generalizes, that takes any new sequence in VDagger and gives it a real value, a number, a scalar. And that number, that value p, think of it as a measure of plausibility. The higher it is, the more plausible, the more fluent, the more language-like the sentence is. That's it. That's language modeling. So the rest of the lecture, now that you know what language modeling is, it's essentially estimating a probability distribution over sequences from data. We're going to talk first about how we evaluate language models, how we know that one language model is better than another. It's a very hot topic these days. We're going to then talk about how we build them. And then we're going to talk about a little bit about how we use them. We don't have to say very much about how we use them. Who used a language model in the past 24 hours? You can admit it. It's OK. I did too. I actually had a language model check this lecture. It's like, is there anything I'm missing since last year? And it was like, you could add some citations. That was about it. OK, so I'm going to add just one more little constraint on this probabilistic language model story, which is kind of important for a number of reasons. P, I didn't tell you this before. I said P was just going to assign every sequence in VDagger some value. But there's a constraint that we put on these values. And it's essentially just the constraint that the P values form a probability distribution. So what that means is that for every sequence X in VDagger, by the way, I make the X boldface to remind me that it's a sequence, but it's still lowercase. It's a particular value of a random variable over VDagger. So for every possible value, every possible sequence of words, the probability can't be negative. And if I sum up over all the sequences what the probabilities are, they have to add up to 1. That's what makes it a probability distribution. And why do we do this? Well, the first reason is that people seem to have some intuitions about probability. I don't know, these days I'm skeptical of most claims about interpretability. But it does seem to be the case that people understand at some fundamental level what it means to put a probability distribution over things. But I think the deeper reason that we make language models this way, and we don't just make it an arbitrary number, is that we can use this tool from statistics called the maximum likelihood principle as a starting point for how we build a language model from data. This is an old idea. We'll quickly review it in the context of language models. But it's been widely useful, and it's kind of the starting point anytime you want to build a scoring function over data. It's a good place to start. At the end of the day, you could argue whether we do maximum likelihood. I think building language models has gotten incredibly complicated, but I think under most of the things that you do, you can find some maximum likelihood style thinking going on. So the idea in maximum likelihood is if you have data, you have observations. Again, for language modeling, this is a big, long sequence of trillions of words. If we have a set script P of all the possible probability distributions that are consistent with our assumptions about the data, then you should pick the one that maximizes the probability of the data that you have. This is familiar? Have you heard it stated this way before? This is like a very mathy way of saying something that most people find incredibly intuitive. When we drill down one level and put this in the context of modern machine learning, typically the way we talk about consistent with your assumptions about the data, we actually translate that into, this is a family of probabilistic models with a particular set of parameters. And so once you've made this choice, the problem transforms a little bit, and we're actually choosing the parameters from among the parameters that are valid parameters for that model. So now we're doing essentially the same thing, but instead of optimizing over this like set of hypotheses, which is kind of cumbersome and hard to talk about, we end up turning this into a continuous optimization problem. And today, with the kinds of distributions that we work with, we typically have a set of tools, which you have seen over the past few days, I believe, stochastic gradient descent, and similar algorithms that let you solve this problem approximately in a fairly efficient way. So we're not going to spend a lot of time on how you do this optimization. I'm assuming that you're familiar with those tools already. But I want to give an example to give you a sense of why this maximum likelihood thing. It's so intuitive that people kind of forget that there are mathematical reasons to do it. So let's turn to the absolute simplest kind of language model, a coin. Okay, so a coin, you can think of it as, if you're going to flip a coin repeatedly, you can think of it as a way of generating a sequence in the language H or T over and over again. Right? You have sequences of H's and T's. H and T is my vocabulary. And I'm going to keep flipping the coin for some fixed number of flips. And so the assumption that we make, we always have to start with assumptions, is that when I flip the coin, each time, there's no memory of what happened on previous flips. The coin doesn't remember anything. The coin is just the same coin. And every time you flip it, it has the same distribution over what could happen. So we're getting independent and identically distributed flips. So the probability that it comes up heads is just some value theta between 0 and 1. That's the single parameter of the distribution. And if you do a little bit of math, you can see if I write this is the likelihood of the data that I have. I multiply in for every flip either a theta if it came up heads or a 1 minus theta if it came up tails. That's the likelihood expression. If I maximize that, there's a closed form solution. I'm not going to derive it here. You have to use a Lagrangian multiplier to make it all work out. But basically, what you get is the very, very intuitive and extremely natural and familiar count up the number of heads you got, divide that by the total number of flips, and that's your maximum likelihood estimate for theta. It's a very, like count up how many times you saw heads and divide by n. I think this is the kind of thing that like you learned this at some point in your life, and it's probably so deeply intuitive that you don't think, oh, how would I do this with maximum likelihood? You just kind of jump to this conclusion that the probability should be proportional to how often you saw the outcome. And so for binomial and more generally multinomial event-based probabilistic models, maximum likelihood estimation didn't even require using gradient descent algorithms. It was just closed form. Count up the number of times you see things and normalize. And there was, if you can believe it, there was a period in the history of NLP where we built all kinds of models just by doing this. You'd start with some data that showed you everything you needed to know that you needed to model, and then you counted stuff up and normalized it, and you built little local probability distributions of things, and you could put those together to form models that did all kinds of interesting NLP tasks. There were no neural nets at this point. Okay, so let's talk now that we've gotten the probability stuff nailed down. We're going to build a probabilistic language model. We're going to use the maximum likelihood principle or something very similar to estimate the parameters. I want to come back to this idea of surprise. This is going back to Shannon, and I think Leon even talked a little bit about this work last night. All things equal, we should prefer a language model that's less surprised by new data that wasn't used to build it. To put this in practical terms, if you have a language model and I have a language model, a fair test would be let's meet tomorrow morning. We lock our parameters and we read the New York Times or your favorite newspaper first thing in the morning, and we check check under each language model what probability does it assign to the text in the New York Times first thing in the morning. We know that this is fair because that news didn't exist when we trained our language models. It's totally fresh new data. And so the language model that gives the higher probability to that data is the winner, the one that is less surprised. So what we need is a way to arrive at this measurement of surprise. And this is how we do it. We take new data. So I'm using X bar to remind me that this is different from my training data. And I calculate the probability of that test data under the model. And just going to point out that this is going to be a tiny, tiny little number. Remember that P is assigning probability to every possible sequence that could ever happen, both the fluent ones and the ones that are not fluent, right? So this is, we're assuming that our probability distribution is not sparse. And so what you're going to have is, regardless of how well that distribution fits the data, as you get longer and longer test sequence, you're going to see an exponential decrease in the size of this probability. It's just going to be a magnificently small number. And so what we do is we transform that number with this very odd-looking transformation. We take the inverse of the probability, and then we take the n-barth root. Okay, you'll see why this kind of makes sense a little later. But basically, you should imagine that what I'm doing when I take the inverse is I'm taking a tiny number and I'm making it really, really big. And then when I take the nth root, I'm taking kind of a geometric average per word in the sequence. And that's perplexity. You can write this a couple different ways. You can rewrite it. I kind of like writing it this way. I like taking the log of the probability. I like log-based too because I'm a computer scientist. Negating that log, dividing by the size of the data. So this is like the average cross entropy, if you're familiar with cross entropy loss. And then I'm exponentiating it. And just another way to think about perplexity. To give you some intuition about perplexity and why we like it as a measure, lower is better. Lower perplexity means lower surprise, right? So a better model will have a lower perplexity. If the model were to put all of its probability on the test data, so somehow magically you built a language model yesterday that predicted exactly what the test would be. It reasoned, in the process of building a language model, you reasoned about everything happening in the world, and you bet correctly on exactly what the New York Times was going to say the next morning, then you would get perplexity 1. If anybody reports to you that they got perplexity 1, you should be suspicious. And the closer the numbers get to 1, the more suspicious you should be. Conversely, if the model really screws up and puts 0 probability on the test data, it totally didn't see it coming, okay? Usually this happens because you have a bug in your training. Perplexity will be infinite because you have a 0 down here, right? So 1 over 0 tends to infinity. So this is one of the reasons, by the way, that a huge amount of effort in language modeling for many years went into the problem of making sure that the probability distribution was always strictly positive, no matter what sequence of words, no matter how ungrammatical, misspellings, ungrammaticality, anything at all needs to get a non-zero probability. Otherwise, your perplexity will go to infinity, and you won't really be able to compare your model to anybody else. You'll just look bad. Anyway, one sort of intuitive way to think about the perplexity here is, because what you're doing when you take this root here, or dividing by n in the log space, is you're getting kind of an average per word. And one way to think about that average is, on average, when the language model is trying to predict what's next, it has a distribution over each word. And it's not choosing really over the whole vocabulary. It is technically, but it's assigning very low probability to many words. So when it's choosing the next word, how many words is it effectively choosing among? And if it always is very confident about the next word, it's like kind of deterministic. It just sort of knows what the next word is every time, then it's closer to 1. But if it's really unsure and it's constantly guessing almost at random what the next word will be, then the perplexity will tend towards the size of the vocabulary. So this is sort of an upper bound. It is an upper bound, the size of the vocabulary. If you see somebody report a perplexity of a language model that is higher than the vocabulary size, you should also be suspicious. There's something going wrong in their calculations, because it shouldn't ever be higher than the size of V. That's a really bad language model. It's effectively guessing uniformly at random. Okay, so a couple of things to say about perplexity. You can only directly compare perplexity of models that have the same vocabulary. If you have 2 models that don't carve up the world into the same vocabulary, there are some tricks. So if you've heard this expression, bits per byte, that is an attempt to kind of transform perplexities from models with different vocabularies so that they can be compared. It's more or less safe. People often report perplexities on test sets in research papers, and they've been doing this for almost 50 years. This is an old practice. It dates back to the late 70s. And the numbers have generally been going down, but you can't compare all of them because the vocabulary sizes have changed. The data sets we compare on have changed. I'm not going to get into actual numbers. 1, because I don't want to change my slides every year, and 2, because perplexity is not really the final goal, especially now that language models are being put into products. Perplexity is just sort of a nice intrinsic measure of the overall quality of a language model on some data that you've chosen. I think it's more important to understand what's changing in the models, in their design, in the data that they're trained on, and so on, than to remember how well they do on specific data sets. It's really important to remember that a perplexity number is always relative to a particular test set that somebody chose. And it's going to be very different on different test sets. So you can go look up numbers in the literature. I think you should take them with a grain of salt. We did this project a few years ago called Paloma, where we collected a whole bunch of different test sets. I think it was like 500 different test sets to evaluate how perplexity varied for different models under different testing conditions. And so thinking about it, again, the point, beautiful point Leon made last night, thinking about like a single distribution that you're going to use to draw your tests from, I think these days it's not super helpful. We're going to use language models for lots of different things. Different tests are going to give you different information about whether a model is better or worse in a particular way. Okay, a point to reflect on while I take a sip of water. We can measure perplexity on any data at all, including the training data. So here just to help make sure you understand, if we measured perplexity on the training data for a given model, do you think it would be lower than the test perplexity or higher? And why? Think about it for a minute. Who says higher? Why? It's going to be worse than the test set? It's going to be worse on the test set. Perplexity will be lower on the training set. Okay, that was the opposite. That's the right answer. That's what you would expect. Because that's the model that, I mean, if we go back to maximum likelihood, right, what are we doing? We're maximizing the likelihood of the training data. That was the whole goal. And what are we calculating when we do perplexity? We're calculating the probability, the likelihood of the data. So if we plug in the training data here, this is exactly what we trained the model to be good at. So the perplexity will be low on the training data. It will probably be lower on the training data than on anything else by design. This is why it's not really that interesting to measure the perplexity on the training data as a measure of the quality of the model. This is just measuring how well did I do on training my model. I want to pause and talk about the vocabulary. This is an underappreciated and delightful topic if you're a language person, which we all are because we all speak language. How do I design my vocabulary? If you are a speaker of a Western language like English or Portuguese, a natural thing that comes into your mind when you think about the vocabulary is to say, well, we usually think in words. We put words in the dictionary. And we separate the words with white space in English and Portuguese. We don't do this in every language. But for those languages, we could use white space as a delimiter and essentially just split the text based on wherever there's white space. And anything that's a token, after we've split our data that way, becomes a vocabulary element, which we can call, sometimes we call vocabulary elements types. The problem with this is that on real data, the vocabulary will be absolutely huge. There are a lot of words, especially in Portuguese, because you have inflective morphology. And they're all going to have many different variants because sometimes they're capitalized, sometimes they're all caps, sometimes they're misspelled, sometimes they have punctuation on the end. And some languages don't even use white space at all. So for those languages, this won't work. So this is generally not how we do it. There were times when people thought about doing things this way. But that's not usually what we do. There's another extreme, which is a very aggressive way to split text, which is to say, at the end of the day, it's all encoded as bytes, right? It's all usually Unicode, but basically you can always break down the text sequence at the byte level. And this is great because how many bytes are there in the vocabulary? How many distinct bytes can you write down? A byte is 8 bits. 2 to the 8, which is 256. So your vocabulary size would be 256. That's it. That's quite small. That's nice. And it might work. The problem with this is that it really does violence to the data, right? You and I do not perceive language as a sequence of bytes, right? The vocabularies we work in, imagine having to use the byte sequence to look up a word in the dictionary. It would be very tedious. Basically, you're making very, very long sequences, and you're fragmenting the data into tiny, tiny little pieces. And so the regularities that we have in natural language are going to be harder to find for a statistical model. So most people don't do this. I won't say this is completely crazy. There are some approaches to language modeling these days that go down to the byte level. But what we do most of the time, what the vast majority of models you've worked with do, is something kind of in the middle that's kind of beautiful. And I just want to give it to you in brief so that you know that this topic exists and you can go learn more if you want to. The topic, by the way, is called tokenization. How do I tokenize or segment my data into vocabulary items? Okay, the conventional solution is you start with data and you learn a series of rules starting from bytes or characters that iteratively merge common sequences into larger units. So really simply, you start out with every byte is in the vocabulary, and then you look for the most frequent sequence of 2 bytes, and you merge that and you add it to the vocabulary. And everywhere you see it in the data, you convert that pair into that single new vocabulary item. And you just repeat this until you have the vocabulary size that you want. There's a couple more nuances to this. I'm not giving you all the details. It's an old idea that actually came out of the compression literature. I should put the 1994 citation on here as well. It came into NLP about 10 years ago, and it's known as byte pair encoding. And there's a couple other techniques that are similar, but this is the basic one that underlies most models. It's quite beautiful, quite simple, and it works really well. And it's what's perfectly delightful about it is that it's safe, because you started with every byte in the vocabulary. Anytime you see something new that's different from anything you saw before, a totally new word, you can always fall back to byte level tokenization. You always have a safe answer to breaking the thing into a sequence. So even if you train your language model on a collection of languages and now you've got text in a totally new language, you don't have to worry. You will be able to represent that new sequence as a sequence of tokens from your vocabulary. It might be really fragmented and ugly and get poor probability, and you'll probably perform badly on that language, but you will at least be able to represent it and give it a probability. Okay, so here's our world so far. We're interested in probabilistic language models with a fixed finite vocabulary V. To train them, we're going to start from the maximum likelihood principle and trust what our friends, the statisticians, have been telling us for over 100 years. We're going to have a training data of like trillions of tokens, and we're going to evaluate, among other things, we'll evaluate perplexity on some test data, and that will be how we guide our performance and know whether we're performing well when we have to compete with another lab's language model. That's the game. Any questions right now? Anything you feel like I'm missing? Yeah.
Alternative view where we can use like Shannon's entropy over the over the logit probabilities in the output space.
Shannon's entropy over the probability of the next word.
Yeah.
So if we go back, here's perplexity. Perplexity is concerned only with the probability of this test data. You could measure what is the entropy of the distribution over the next word at each point, or take an average or something like that. I'm not sure all that would be measured. What that would be measuring is how confident is the model, right? You could measure the entropy without any test data at all. And you could cheat and get really good entropy by making your probability distribution always prefer a particular word. You'd have very low entropy. Make sense?
Yeah.
And you could cheat and make the entropy really high by always having a uniform distribution over the next word. So I think entropy has its uses, but here it doesn't give you the distribution. It doesn't give you a sense of how well the model fits data or how well it predicts.
Yeah, thanks.
There's one down here. Can we cheat at perplexity? Or is it a... So here's the thing about perplexity. I think basically there is a way to cheat, which is to feed your test data into the model. But that's like really blatant cheating, right? And if we come up with test data that, like tomorrow's New York Times, that you really couldn't have guessed, then I think the answer is basically no. People have, in 50 years, I don't think people, apart from the really blatant cheating, or it's usually when people screw this up, it's usually like a poor grad student who just made a mistake, right? It wasn't intentional. But that is, that is a thing you have to watch out for. But I think beyond that mistake of feeding your test data in to train the model, I think it's probably pretty hard to game Perplexity. Is it a good measure? I think it's an appealing measure for scientific reproducibility. It's an appealing measure for those of us who want to think kind of like statisticians. But it's not the true measure, right? What's the true measure of the quality of a language model? Do people use it effectively to do the things they want to do with it, right? And that's a very complicated, high-dimensional, messy human question, right? We have a lot of other things that we use to measure language models, right? We have tons and tons of benchmarks to measure different capabilities on different kinds of tasks, right? We have ways of measuring how well a language model translates text. We have ways of measuring factuality. We have ways of measuring whether the model is overly sycophantic. We have ways of measuring whether it generates hate speech, and so on, and so on, and so on, and all kinds of things that we want from language models. And I think that work is important because those things approximate the experience of a human who's going to use the model at the end of the day. But there's so many of them. And many of them can actually be kind of reduced to choosing a test set for Perplexity. So coming back to Perplexity, I think, is always kind of an appealing base to start from. I think as scientists, Perplexity has a certain appeal, but I don't think it's complete, and I don't think it's the final game. The final game has to do with, does it serve humans? Okay, one more, yeah.
You mentioned that the thing that we use most of the times, or the best test, would be news. Is there anything else that we can use, especially for LLMs that we don't know the training data on? A lot of, the proprietary models don't say what they train their data on.
Yep.
So the only option would be news because we are sure they have
News something, right? It doesn't have to be news. It could be a new conversation that we have on a new day. But I think that's right. If you don't know what the training data was, you have to find a source of fresh data that the model could never have seen. Yeah. This is a big pet peeve of mine, that we don't know what the models were trained on, right? This motivates a lot of my current work in building fully open models. I want models available where I can test, was this test data actually in the training set or not? Okay, I'm going to keep going in the interest of time so that we are not late for our appointment with the photographer. Okay, we talked about the vocabulary. That's our universe. So here's your first language model. We are going to assign the probability to a sequence X by looking at how many times it occurred and assigning the probability proportional to the number of times that sequence occurred in our training data. Follows the maximum likelihood principle. This is very sensible. This is what we would come up with if we didn't know everything we learned yesterday and the day before. Kind of nice. We're done. No. Okay. Here's the problem. What if the test data, the new sequence I want to assign a probability to, is not in the training data, as it should not be, as we just discussed? What's going to happen? If it's not in the training data, what's its count? 0. The issue remains, even if we take a more nuanced view and think of the training data as a whole bunch of different sequences, if it's not there, and you get a 0. So I call this the creepy language model. It can only assign probability to things it's seen before. It has not generalized at all. It's not useful. Nobody ever talks about it. And it's, other people who teach language modeling think it's absurd that I even put this in my slides. But I think it's useful to pause and think, why don't we just count? This helps us understand why pretty much every language model today that you've interacted with, maybe not 100% of language models, I guess diffusion models don't work this way, uses the chain rule. Pretty much every model that we interact with uses the chain rule. This is sometimes called autoregressive. The idea is that you break down this sequence. Think of your probability over sequences. There's a big random variable, bold X, over all sequences in VDagger, and we decompose it word by word, token by token. First, there's a probability of the first one. Then there's a probability of the second one given the first one. Then there's the probability of the third given the first two, all the way up to the probability of the stop given all of the n-1 tokens that came before. The elegant way to write it is this way: probability of the ith word given everything that came before. multiplied together over all the words. This is just the chain rule. We saw it earlier in the lecture, and it elegantly breaks the problem down into the word-by-word problem that we see in autocorrect and that, again, most language models today use. Once you decide that you're going to do language modeling this way, the game becomes, how do I summarize all of the relevant information about the history? I'm going to use that term history to refer to the words that come before. Sometimes people call it context. I want to summarize all the information that I need from that history to predict the next word. That's the goal. Okay, so here are some historical language models, no pun intended, that it's good to know about because they made different choices about how to summarize the history. The first one is called the unigram model. It goes back to Shannon, and it says, use the chain rule and then make an assumption that the probability of each word does not depend on the history at all. So this is kind of like my memoryless coin that I was flipping when I talked about MLE. Now you can think of it as like a die, like in games of dice, you play at a casino. The die has V different sides. Every word is written on a different side, and I just roll the die over and over again until I roll stop. And so I can think of this as a parameterized model where there's a theta for every word. That is the probability of that word conditioned on simply the fact that I'm rolling the die one more time. And this is a very simple model. It doesn't require gradient descent. It has a closed form solution because you're basically saying, instead of counting sequences, I'm going to count words. How many times did each word occur in my training data? I count it up. I divide by the total number of words in my training data, and those are my parameters. That's all I have to do, closed form. Really, really simple, beautiful, really bad model of how we generate language. I think, maybe not for some people. Most people, I don't think, generate language this way. So the probability of presidents tell lies is you have the probability that one of the words, that the first word is president, times the probability the second word is tell, times the probability that the third word is lies, and so on, up to the stop symbol at the end. Each of these is an IID event, so you have you simply pick the right element of this theta vector for each of the words, you multiply them together, and if you wanted to estimate them, you would just count up the number of times you saw each one in the data, divide each one by n. That's it. Very, very simple, very easy. You could write probably less than 10 lines of Python to estimate this from any amount of data. You can distribute this across lots and lots of computers. You don't even need GPUs. You can use CPUs for this. In fact, you could do that. You could estimate this without data. I could imagine sitting down for a few hours and just thinking, how frequent do I think each of these words is, and estimating the probability by hand. It would take you a while because there's a lot of words. But I want you to think for a moment about a language model where you didn't even use the data. You just said, I'm going to make it an equally weighted die. Every word is equiprobable, so each one gets probability 1 over V for everything in the vocabulary. What will the perplexity of this model be? Doesn't matter. Hint, it does not matter what the test data is. As long as the test data is words in the vocabulary, it doesn't matter. What will be the perplexity? Someone in the back? V. It'll be V. Because if the probability is always 1 over V, you multiply that together once for every word in the data, and then you take that same root, n, of that huge product, and you get back V. There's an inverse in there. I forgot the inverse. So this is like the worst possible language model you could build that gets perplexity that's finite. It doesn't put 0 on anything, but it's just completely agnostic. Oh, there's the math, right? I plug in 1 over V for each of the probabilities, so there's n bar of them. These guys cancel, and I get back V. Okay, so unigram models, the simplest language model that actually had any impact in the research field. Extremely simple, extremely easy to build, extremely cheap to build. They formed for a while before pre-Google. They formed the basis for some kinds of information retrieval or search for documents. But but they make some really bad assumptions. The first one is, of course, this known vocabulary assumption, which pretty much every language model makes. But they make this assumption that language is basically a bag of words, and this is just linguistically inaccurate. The most common word in English usually is the in most data sets. And so this means that the probability of just a whole sequence of thes over and over and over again is going to be higher than any linguistically valid sentence you can think of the same length, because the always has the highest probability. It's just broken. It's not a great model of fluency. So very naturally, the next thing to consider, and Shannon was thinking about this back in the 40s, is condition on the most recent words. And so these are called Markov models because they make a Markov assumption. Sometimes they're called n-gram models. That's the more common name in the NLP community. The idea is that you condition each word on the n-1 words that came before it. Sorry that this is a little dense, but it's basically saying go back n words plus 1 and go up to the word right before. That's my history. It's a finite history of n-1 words. So you're making an n-1th order Markov assumption, which we call the simpler name is n-gram model. The n-gram is the n-1 words before plus the word that I'm predicting. Unigram model is a special case of this where n equals 1 and there's 0 words in the history. And the idea is quite simple. It's a simple generalization of what we saw before. You can estimate it with counting and normalizing, as I think I'll show in the next slide. And for a long time, it was really hard to beat n-gram models with n equals 3. And then when I was a student, so like 20 years ago, n started getting bigger. And we were getting better results with longer n. Why do you think that was the case? Why was it that n equals 3 was great for a long time, and then suddenly it was like, oh, no, use n equals 4 or 5. It's better. What changed? Over here? Increase in training data. The key insight about n-gram models is that as you increase n, you need more data. We'll talk more about why that's the case. What's the maximum likelihood estimate for the n-gram model's probability of some word v given it a history h? We're going to use the same principle as before. What we're interested in is the conditional probability of v, of xi, random variable, taking a value v from the vocabulary, given a history h. H is going to be a sequence of n-1 words. Okay, this is kind of dense, but I like to spell everything out carefully so that you can check it later and make sure you fully understand. Remember that conditional probabilities can be written as a ratio of a joint probability up on the top divided by the marginal probability of the value on the right side of the conditional bar. So each of these is a probability over some events. And the first one is the number of times I saw the history together with the word divided by n. That's my maximum likelihood estimate for the joint probability of this n-gram HV. And then I have a shorter n-1 gram, and I estimate it the same way. How many times did it occur divided by the number of times I saw a sequence of that length. If I take this ratio, the n's cancel, and I get a ratio of counts. A common mistake is to forget that this is a conditional probability. And so if you build an n-gram model by just estimating the probability of the joint, you're going to underestimate everything. You're going to have tiny probabilities for everything. You'll get terrible perplexity. So don't do that. Remember that it's a conditional probability if you ever have to build one of these. Okay, so but this formula helps us see why we need more data as the history gets longer. Think about how many different history word combinations you're going to see in the data. If you have a small amount of data, you're just not going to see very many of them. As the history gets longer, you're going to have more and more zeros. Your estimates are going to be sparse. Your data is sparse. So in order to make sure that I've seen lots and lots of histories with each word, or to put it the other way, lots of words with each history, and get a good estimate of this whole distribution for every history, I just need more and more data. What was happening when I was a student? The web was growing. The amount of data available for building things like language models was getting bigger and bigger and bigger. for more and more languages. That's still happening today, but it was really happening in the late 90s and early 2000s. So, one of the big things Google was really good at was taking all that data and figuring out how to use it. And one of the ways they used it was to build n-gram language models. About 20 years ago, there were keynote talks at conferences about building bigger and bigger language models, if you can believe it, using more data from the web. Okay, I want you to think for a second. Imagine that I give you a new sequence of words and I ask you to calculate its n-gram probability. Let's say we're doing a test and we want to know how well would an n-gram model do on Perplexity with this data. To make this procedure as fast as possible, what would you want for this data structure that stores the probabilities? What properties should it have? What kind of data structure am I going to use for this? Any ideas? A tree. Why a tree? You're prescribing the answer, but tell me why a tree.
We are trying to store the probabilities of sequences and its prefixes as well.
Yeah.
So a tree would be nice because we can store them as one word.
Yeah.
Then its children are the next words of that word.
Yep.
And so on. So it's
I
really
think
nice.
the property that leads you to the tree.
Composition.
You want constant time lookup.
Okay. Yeah.
Right. Like, given that the n-gram is always the same length, you want to spend a constant amount of time looking up. You don't want to have to do more computation for some of these things than for others. You want it to be a fast lookup. I think that's the most important thing. It is true that people use things like suffix trees and so on. One of the interesting properties is that notice that you have to be able to, if you're looking up counts, if you're estimating the probabilities on the fly by taking ratios of counts, then you need to look up two different related n-grams. One is the n-gram, which is the sequence of the history plus the word. The other is the sequence of just the history. So you want those, if you want to make those two things close together, using a tree structure would help you. So people did in fact use different kinds of tree structures for these things. Okay, so back to this point about n-grams and how you might choose the length n you might use to build your n-gram model. The tension here, we talked about what happens if you don't have enough data. The other end of the spectrum is like moving back towards the unigram model. If you make n very small, then your model can't learn very much about language. It doesn't really get a lot of patterns, right? All it can do is learn at the most what the relative frequencies are of the words. As you increase n, you get more parameters, and that the number of parameters that you might need in principle grows exponentially. But the number that you're actually going to be able to store only grows effectively with your training data. So basically, most n-grams are never going to be observed, and you're going to have a whole lot of zero probabilities in this count table or tree or whatever data structure you use. So we call this data sparsity. People use the word sparsity a lot in machine learning. Sometimes it's a good thing. This kind is not a good thing. Data sparsity hurts you. It means most of the events that you might care about on test day, you never saw. So your model, as you increase n, what your model learns depends more and more on the training data, and you need more and more data to learn to generalize well. Did the machine learning lecture talk about the bias variance trade-off? Good. Okay. This is a beautiful, beautiful, probably my favorite illustration of the bias variance trade-off. And that leads me to this picture, which we'll come back to a few times in the talk. So now we've basically covered history of language models up to the end of the last century, the end of the last millennium. But already you can see in broad strokes what the research landscape is going to look like. So I'm going to walk through this. I know there's a lot on this slide. We have a language model. There are different things that we can do to it that might change how it performs and how much we like it and whether it's a good model. One thing that we might do is increase its capacity by giving it a larger n if it's an n-gram model, giving it longer histories to look at. If we do that, we're going to immediately see three things. The first, the obvious one, is we'll have more parameters. We have to store more counts because now we have way more n-grams. That number of n-grams that we could potentially see goes up exponentially. It's going to cost more to store those parameters. It's going to cost us probably more to do lookups of longer n-grams, maybe not a lot more, but a little bit. But in return for that, we're going to get a better fit to the training data at least, right? The longer the n-grams I can see, the better I can fit my training data. And maybe that will generalize to better test perplexity. And maybe, just maybe, that means I have a better model in applications. These things are always a little uncertain. Sometimes you get a better fit to the training data, but you don't actually do better on the test because you overfit to the training data. Your generalization can get worse if you overdo it. So this is a dashed line and a question mark. Sometimes you get better test perplexity, but the model doesn't actually work better in applications. No guarantees. So you really should evaluate it. Okay, so maybe when I increase the model capacity, I get better generalization. Maybe that's a good thing. Maybe I've learned something and I've advanced knowledge, and now I know something new about language or about how to build systems that serve people better. Maybe, but all of these dashed lines are sort of possibly, should probably check, not given. Another thing I might be able to do when I'm building a language model is just train it on more data. This was the experience we were having in the 90s and early 2000s. As the web was getting bigger, we could train the same model on more data. That costs more computationally. Again, not much for the n-gram model. It scales very nicely with the data. And maybe that led to better generalization. Usually it did. Usually more data is a good thing. And the same things hold. Like maybe you're getting better generalization, but you have to kind of go check. And there are ways to make your model better and get better generalization that don't really contribute to new knowledge. Like, it's been known for a long time that adding more data is going to make your model generalize better. That doesn't really contribute anything new in terms of the science of language modeling. So this is, generally not a very exciting way to make an improvement. You're not going to get famous by saying, "Oh, I added data and it made my language model generalize better," right? There's another thing you can do, which we haven't really talked about, which is you have your language model and you somehow change its assumptions. You somehow make it more biased in a good way so that inductive bias is helping you learn a better model. I haven't given you any tools for doing that, and some of what we see in the rest of the lecture might be doing that. But basically, this is like a play that people tried to make many times in the history of language modeling. Like, is there something more I can bake into this model that will make it generalize better beyond simply giving it more n-grams or larger data? I think you can still use this slide today to make sense of what research contributions are in the space of language modeling. What are some things that people did do to improve inductive bias? I want to spend a minute on this. The big thing, most language modeling research up until the neural phase was really about this one problem of trying to make sure that you never had zeros for any n-gram and keeping the probability so that it summed to 1. And people came up with all kinds of techniques. The dead simplest, which it's much older than 2019. This is a textbook that gives it, for the first time I saw this name, Lidstone smoothing. The idea is you pick a value lambda, it's positive, and you simply add it to every single count, including the zero counts, before you normalize your probability distribution. You can justify this on some mathematical grounds. It doesn't work particularly well, but it's dead simple. And it's kind of a starting point for thinking about this problem we called smoothing. Smoothing is basically figuring out, how do I make sure that the probability mass is never 0 for any n-gram? After many years of research in this area, there was a method called Kneser-Nye. It's more than 30 years old, and it's still kind of the default. If anybody is ever going to compare to an n-gram language model, they're probably going to use a version of Kneser-Nye smoothing that was a small change developed by Chen and Goodman in '98. Interestingly, the folks at Google they wanted to solve smoothing, but they didn't really care about perplexity. And so they were okay with giving up some probability mass and not having things sum perfectly to 1. And they came up with a really simple solution they called stupid backoff, which was really easy to parallelize. So if your data is spread out over thousands and thousands of computers, and you want to do all the language modeling computation by counting things locally and then summing up the counts with a programming model that was called MapReduce, you could do this stupid trick, which gave you smoothing, but it didn't always sum to 1. And they found that this was fantastic. It worked fantastically well. Obviously, they couldn't measure perplexity, but they could measure other things, like how well did it perform on machine translation. And they found that this helped. It was as good as other things, and it was super easy to implement. So you can guess what they did. This leads to this sort of smoothing thing. So the idea is that when you're doing smoothing, you're adding inductive bias to your model. You're saying that nothing should ever be 0, and the different methods for smoothing were basically different stories about why it shouldn't be 0 and how you should make sure that it was never going to be 0. But you always had to pick some hyperparameters. So for example, with that simple add lambda lidstone smoothing idea, you had to choose. You had this micro decision. What value of lambda should I use? And this illustrates a problem that comes up again and again and again in machine learning and AI, which is, how do I set my hyperparameters? There's always something in the system where I've got a knob, I've got a turn, and it affects how well the model, it clearly has an effect on how well the model will do. If I make lambda too high, then I don't learn as much. If I make lambda too low, I move back towards overfitting, and I get closer to having zeros. These choices are usually, these hyperparameter choices, they're usually not very interesting. Like, there's nothing deeply intellectual when somebody like you've learned something, right? It's not satisfying. It's just like, oh, they did some experiments, they picked this number empirically. They're not interesting on their own. We don't have good a priori reasons. It's not like, you know, I studied for many years and I thought about it and I came up with 0.7, right? It's not wisdom. It's like, we looked at experiments, we look at what people have published in the past, we talked to a senior grad student in the lab, and they're like, yeah, 0.7 works pretty well, try that. And so this is like usually just kind of experimental, and it's important because you've got to pick your hyperparameters. You can't run the experiment without doing it, but they're kind of a nuisance. So I want to give you the one rule about hyperparameters that everybody needs to know. You can try different values. You can pick one, but you have to use something called a validation data set. This is a data set that is separate from your training data and separate from your testing data. If you use the training data, then you probably won't pick hyperparameter values that generalize well. You're going to pick the values that give you the best likelihood on your training data. You use your training data, you'll pick lambda equals 0 because it never helps training data likelihood to smooth. It's always better not to smooth. You also never use the test set because that's cheating. That's a way of letting the future test influence the way you build your model. It's like reading tomorrow's paper. You shouldn't be able to do it. It invalidates the test. So it's always wise when you're building data sets to keep some data held aside that you're not going to use to train and you're not going to use to test, because you're going to realize down the road at some point, oh, there was a hyperparameter here. I need some way to make this choice. Hyperparameter tuning is usually kind of seen as thankless work, but I think as we move more and more towards thinking of language modeling as an important scientific pursuit that has huge implications, we really should think about this as something that we want to do in a systematic and replicable way. In other words, you don't want the grad student to just say 0.7 worked for me. You want them to be able to report the entire procedure they used to get to 0.7. And there are ways to do this. It's called hyperparameter search. People often use randomized methods to search. We wrote a paper called Show Your Work that basically argued this is something everybody should talk openly about, because often a lot of computation goes into choosing the hyperparameters that isn't reported, and then people don't understand exactly what the cost of building a system was. Okay, I could talk about that all day. Ngram models, you know, easy to understand, pretty cheap. They worked pretty well in many settings. They were the best thing going up until 20 years ago or so. They still make this known vocabulary assumption. That hasn't changed. That won't change today. they make this Markov assumption that's not as bad as the unigram models, but it still seems wrong. There's still this conditional independence between the history, more than n words in the past, and your current word. And that seems wrong. That's not how language works. Anyone who's studied linguistics knows that language has structure. Conversations do depend on things that happen much farther earlier on in the conversation. And we have this data sparseness problem that necessitated all this work on smoothing and introduced weird hyperparameters that nobody had really good intuitions about. So that leads us to a big change. And it didn't happen overnight. Neural language models took some time before they caught on. And we'll see why. But basically, the idea of building a neural language model is essentially to say that this same probability distribution, so this doesn't change. We still are estimating the probability of the next word given some history. We're going to use a neural network to give us that distribution. So we're going to somehow encode the history in some way and then use a neural net to decide, based on the history, how do I map that history to a distribution over the next words? So the parameters here are going to do the work of encoding the history and transforming it into a distribution over the next word. And usually, I don't know if other people gave you a definition of a neural network. This is one of these things that everybody seems to know, but it doesn't, it's a function, it has parameters. There's a pretty common structure to neural networks, which is that they have layers, right? They go through certain kinds of transformations. So we'll talk about that a bit in the context of language modeling. So the name, I think, is confusing. I wish they hadn't called them neural networks, honestly. So formally, you have a function that takes learned parameters, theta, and inputs and gives you outputs. And everything in neural net land is real valued vectors. So despite the fact that we are focused on a discrete distribution, on discrete symbolic data, everything inside the neural net has to be continuous. The design of the neural network is pretty much universally such that it will be differentiable with respect to the parameters. Why? So that we can use gradient ascent type methods to train it. And it's going to be nonlinear with respect to the data input. Why? Because that gives us a rich set of functions to approximate the mapping from, in this case, contexts to output distributions over the next word. What does nonlinear mean? Nonlinear means that this neural net encoding for an input v cannot be written as a matrix multiplication. There's something else going on here that makes it more than a linear function. Okay, so for a neural language model, we usually think of this in two stages. One is to encode the word histories into vectors or matrices, and then a way to interpret the output as a probability distribution after we've done some transformations. Okay, so there was a type of language model that really did not catch on at all. This is another kind of idiosyncrasy of my way of teaching language modeling, is that I pause and talk about things that kind of didn't work and talk about why they didn't work, because I think they're useful to fill in some gaps. So this was basically, I don't know, the idea was, it started in the early 90s. And the kind of model that was used here was widely used for other problems in NLP, but it just never caught on for language modeling. And the idea is to think of the problem as classification. So think of your vocabulary as the labels, and then think of language modeling as supervised classification. So you have n instances, one per word in your training data. The input is the history, and the output is the prediction of the next word. And so every word in your training data comes with a history, which is its input, and it is itself the label. And so the idea is to build this classifier. What's interesting about this data set is that the instances are not independent of each other. So it's a little different from the usual classification setup. Each instance overlaps with a bunch of others. But you have a huge amount of data, so we're just not going to worry about it. You could use a technique. My favorite classifier was always multinomial logistic regression. You could use this technique to train a classifier to predict the next word. Multinomial logistic regression says all I have to do is take my output v paired with my input and represent that pairing with some vector of features. I have to decide what those features are going to be. Each feature gets a weight, so I take an inner product of the features with the weights, theta. I exponentiate that to get the score of this next word, and then I renormalize by the sum of the score for every possible alternative word, alternative label I could have picked, and that gives me the probability over the next word. Are people familiar with this kind of model? You covered it. Awesome. Thank you. I knew you would, because you do every year. We have a system. Okay, so that's it. Did this model have another name when Mario covered it? Maxent. People love to call it Maxent. There's good reasons for that, which Mario may have covered. The thing that math people always forget about this is that all the magic is in the features. You have to pick the features of the history and the candidate next word to decide to make this work. All of the magic is in the features. And so people in NLP call these maximum entropy models. They did not call them neural language models. It's slightly controversial for me to call this a neural language model, but I think it is. It has all the properties. It's a nonlinear function. It's got a linear piece here where you're multiplying the parameters by the feature representation. You train it with something like gradient descent, and it's differentiable, so you can use gradient descent. So why didn't they catch on? The main reason they didn't catch on was that what you're doing every single time you run this function, you have to score every word. You have to run every candidate next word through the feature function and calculate its score so that you can renormalize. This was just very expensive in the 1990s. We just didn't have hardware that could do this at a very significant scale. And so these models were pretty much impractical for language modeling. They were used for many, many other things, but not in language modeling so much. They also hadn't quite figured out, it took a long time for people to figure out that this problem was best solved with optimization techniques like SGD. Mario could probably give you better reasons than I could why it took so long to figure out that these general optimization techniques were the right thing. It probably also had to do with the compute. But basically, if you can set up a problem this way, all of the math is there. It took some time for the computational abilities to catch up. So I answered the question. Okay, so this is your first neural language model. It's to just treat the problem as classification, train multinomial logistic regression, and the principles are all there. The math is all there. Nothing really changes fundamentally from the Ngram model. It's just that now there's no closed form solution, and so you're going to pay something computationally, something more than just counting things up and storing tables or trees. But basically, if you recognize that you could have done language modeling this way in principle, and today you could very well build this kind of model if you wanted to. If you were willing to put the time in to design the features, you could totally build a language model this way. The compute would be nothing compared to what we train models with now. I think if you understand this, it makes everything that follows a lot easier, because we're going to see a lot of math on the next few slides. Why are we going to see this huge zoo? They're all going to be cats, by the way. So we start with a cute little kitten, multinomial logistic regression. You can imagine where this is going. The general ideas that you're going to see in the next models have been used across NLP for many problems. Today, we solve pretty much every NLP problem with language models. And in earlier iterations of this summer school, that wasn't true. So we had lectures on specific sequence problems and tree problems in NLP. We don't really cover that now. But I still think the same thing, you're going to see the same thing over and over. Understanding the similarities and differences across the approaches makes it easier to be unsurprised when something new comes along. So there's a meta point here about language modeling, right? If you understand the past, if you see enough training data about the history of the field, then you will not be floored when new language modeling advances come along. You can go back and be like, oh yeah, Noah showed me that slide with the 3 colors. This is an inductive bias thing. Or, oh, they're making a scaling play. It's just more data. Or they're making the model bigger. Those things come back again and again and again. Okay, I think we should maybe see if there are questions before we go on. How are we? Yeah, we're perfect. We have a couple, maybe 2 minutes for questions, and then we'll go do the picture. Back here.
You had to compute the denominator, right? Because you had to, but yeah, but don't you also need to have the numerator, but for multiple v's? So you still have to compute also the numerator multiple times, if you know what I mean.
You have to compute, well, the numerator, if you do the denominator, then you've done the numerator.
Yeah, exactly. That's what I'm saying. So like,
Oh, but it's different. It's different at every history.
okay.
You don't get to reuse it very much.
That's what I mean. Like, I thought
Yeah.
you can reuse it once you know the.
There's not a whole lot of computational reuse with this model. That's why it stinks.
Why can't you reuse it?
Because H is different for every word.
Okay.
Every word has its own history. H is the input, right?
Thanks.
Yeah, good point. Okay, I've deliberately paused at an emotional low. We had n-grams, we tried neural nets. This simple thing isn't going to work because of this summation. That's bad. We're depressed. That way you'll come back, right? If you're producing a telenovela, you want to pause on a low point. Oh. There's one more question here.
This feels like a side question, but since you've complained about the name neural network, if you could change history or like redefine it now, what name would you choose? Have you thought about
I
it?
have an answer to this.
I know it.
You already know what it is. Yeah. I think I said this about almost 10 years ago. I wanted to give a provocative talk, and this was the point. This is around 2017. Was Vancouver 2017? Nobody remembers. ACL was in Vancouver in 2017. Does that sound right? iClear. No, it wasn't iClear. It was ACL. Anyway, I got to give a keynote, and I wanted to be provocative. And this was a point where intellectually I had accepted that neural nets were useful. And the way I thought they were useful was for representation learning, but I still thought we needed structured prediction. And so I gave this talk that put together a lot of my students' work about using neural nets together with structured prediction, which is, I think, still a really cool topic, but a little bit less mainstream now than it was then. And I used this as an opportunity to complain about the name neural networks, and I proposed that a better name was squash networks, because they universally have something called a squashing function that transforms nonlinearly. And so I proposed we call them squash networks. And I had lots of pictures of squash, the food, to drive the point home. And then I gave a talk some months later somewhere, and they gave me a nice gift, which was a cookbook of squash recipes. It did not catch on, but it would have been a better name. I always think it's better when you give things a humble name, so that when they work well, people are like pleasantly surprised. It's like under promise, over deliver. Squash is a humble American food. When you call something squash, nobody's like, oh my God, this is going to change everything, right? We would have loved the machine learning people better if they had been humble, instead of saying, we're building brains. All right, should we go take a picture? All right. What? We changed plans. Tell me the plan.
So you're going to have the coffee break, and in the last part of the coffee break, we're going out to take the picture. So if you want to stop now, you can. Otherwise, you can keep going for a while.
Let's do the coffee break, but we'll come back in time to finish.
Okay, cool.
Okay. So we'll start again. Thanks for coming back. So what we have ahead of us are a bunch of neural language models. Before we get into them, there's a couple of things that we have to talk about that that are important, an important set of tools for moving forward. The first one was sort of a separate stream of work that led directly to the ability to build neural language models that work well, which is to embed words as vectors. So I want to spend a few minutes on that. And the other is going beyond what we saw with multinomial logistic regression, which takes your feature vector representing your context plus your next word, multiplies it by some weights, and then does a nonlinear transformation and repeats that and does layering. So typically neural networks are more layers than just the one. And those two things together are going to get us where we need to be. But some things stay the same. We use stochastic subgradient descent. We use backprop to do the computations necessary to maximize the likelihood. We're just going to kind of repeatedly say, you learned that already, so we don't have to teach it again. One thing that's kind of different and maybe noteworthy is that from here on, the surface of the likelihood function that we're optimizing doesn't have a property anymore that it had up till now. So in the beginning, when we had n-gram models, the likelihood surface was so simple that it had a closed form solution. And then when we moved to the Maxent model or the multinomial logistic regression model, we had to use optimization algorithms, but the surface was convex. It doesn't matter how you initialize. If you run SGD or similar long enough, you'll get close to an optimum, and you can prove that. That's not the case anymore. From here on, we won't have a convex likelihood surface, and so there's just sort of more ways things could potentially go wrong. But let's talk about word vectors before we get to all that. Remember that when we work in neural networks, everything that goes in has to be a vector. And so somehow we have to get from these symbolic things, which we call words in our vocabulary, into some kind of continuous space. And the natural starting place for this is to define what are called one-hot vectors for every word in the vocabulary. So if we have V words in the vocabulary, then we're going to create a single one-hot vector, meaning a single element is 1 and all the others are 0, for every word in the vocabulary. So if we stack these together in order, we get the identity matrix. But we're interpreting it in such a way that each column of that matrix corresponds to one of the words in our vocabulary V. And so this is just sort of notationally convenient because what we're going to do is we're going to start every neural network that takes language in by multiplying that identity matrix. We're going to select an element from the identity matrix corresponding to the word going in and multiply it by a V times D embedding matrix. So what we're doing is we're selecting a vector that's going to embed that particular vocabulary item. We can call it MV. And that's how we're going to represent the words. And people thought a lot about how to do this. There's a lot of history behind word embeddings. The way I think about it now is like these are just more parameters that you have to learn. You have to learn when you learn your neural network how you're going to map every word into a vector. But this idea really fascinated people because it's quite different. The traditional way of thinking about words is more like this: like every word is just different from all the others. And there's nothing shared among them. They're all just different elements of a discrete set. When you start representing them this way, where you look them up in a vector space, you can start having the idea that some words are more similar and some words are farther apart. And words might be similar for different reasons. So we have lots of different dimensions. So two words might be similar in some dimensions, but not others. But anyway, I think people often call these dense word vectors as opposed to the very sparse one-hot way of representing the words. This idea just really fascinated people. And there was a lot of work over the years trying to find out whether when you built word embeddings from data, do they somehow connect to the deeper meanings that people put on these words? And there was I don't know, it was a rich literature around 15 years ago where people got really into this. But we're focused on language models. And this is just sort of a convenient thing to have in your toolkit if you're going to use neural networks to build language models, because again, everything has to be vectors. But again, this idea is much older than neural language models. You can find it going back at least to 1992. And in fact, at one point, I thought, I've had many iterations of teaching language models and NLP more generally. And there was a point when I thought it was useful to start from word vectors and work up to modern language models. And so, different way to do this lecture that I'm not taking today, but I wrote an article about this called something like Putting Words into Computers 5 or 6 years ago. So if you want that take, you can go read it and get a much richer set of connections to past work. So how do you build word vectors? Well, you can do it without language modeling. And in fact, the earliest word vector methods took co-occurrence statistics between words. So they would ask, how often does the word V occur just before or just after or somewhere near another word V prime? And you'd build up a matrix of these co-occurrence statistics. And you could ask questions like, do these two words co-occur more often than we would expect by chance under a unigram model? Or sometimes they would work by trying to build a predictive model of guessing a word at a position given another word nearby. And so this led to things like a method called continuous bag of words and skipgram. There was a popular package called Word2Vec. Have people heard of Word2Vec? Yeah, oh, wow, okay. It's still alive and kicking, I guess. These were basically trained like neural classifiers, and they have a very close relationship to taking a co-occurrence statistics matrix for the words and doing some kind of matrix factorization on it. There's a whole literature on standalone word vectors. And that is one way. I'm going to go slightly out of order here. You use an algorithm like skipgram. You build your matrix of word embeddings and then plug them in and use them in your language model directly. And you could keep them frozen and save yourself the work of training those embedding parameters. This was an idea people used for a while. Another idea is just to initialize those vectors in the language model by pre-training that way. And neither of these has really survived. I think today, the vast majority of the time, people are building language models on large amounts of data. They just treat M as more parameters. They initialize randomly like every other set of parameters, and they learn using the language model likelihood how to represent all the words. But back at a time when computational expense was balanced in a different way, then maybe this was these two things might have been shortcuts. So this idea of pre-training, which today means pre-train your language model before you on likelihood before you change the objective. At one time, it meant something different. It meant pre-train some of the parameters using a simpler method, and then relax and continue training with a different method. Anyway, so word embeddings are a key ingredient. And so what's going to happen when you get a sequence of words, you're going to transform it into a sequence of vectors. And you could think of this as like, okay, we could do this and then use multinomial logistic regression, somehow convert this into features on this stack of history vectors. I think where things start to get interesting is recognizing that when we move to neural nets, it's not immediately obvious how you're going to deal with variable length histories, which is something we didn't really figure out a good way to do that back before we had word vectors. So it still remains to be seen how we're going to do it with word vectors. But basically, up till now, all of our language models have had a Markov assumption. We assume that each word only depends on a finite fixed length history of the most recent words. Okay. The other piece that we need is to add more layers. Neural networks pretty typically have the following look and feel. You compose functions. You take affine transformations, which give you a new vector by multiplying the previous round vector by some weight matrix and maybe adding a bias vector. This can change the dimensionality of the vector from v to v prime. It can get bigger, it can get smaller. You can find all of these attested in the literature. The key thing is that W and B give you some parameters that you can train. So you're learning a projection of the data in the context of the other layers that come before and after. Typically, I think people probably already have this intuition, you're not going to have any way of a clear way to interpret this collection of weights. You can't really look at a parameter of a neural network and immediately understand how it relates to the input-output mapping. Everything is working together. The other piece that's very important is to have nonlinearities. So a common one is the hyperbolic tangent. I'm giving it as an example. This one has a mapping that takes very large negative values and brings them close to -1. Things get interesting around 0, and then after a certain as you move to the right and get to larger high magnitude positive values, you get closer and closer to 1. This is the squashing behavior that I mentioned earlier. There are others. There's rectified linear units, which are just linear on the right-hand side. There's other things like the sigmoid, which map into 0 and 1. There's a whole lot of different possible nonlinearities. Notice that the vast majority of them don't have more parameters. They are literally taking element-wise values and doing a transformation, a monotonic transformation on them that is nonlinear. So what typically happens is we alternate between them. You do some kind of projection, you do something nonlinear. You do another projection, you do something nonlinear. I'm not saying prescriptively that's always what happens, but you read enough neural net papers and this is the pattern you start to see. And the tendency, and there's some theory for this, is that as you increase the capacity, as you increase more layers, you increase the capacity. In other words, you get more parameters, you get more computational costs because it's going to take you more work to do the back prop and calculate your gradients, and you've got more parameters to fit, so it's probably going to take longer to train, but you'll be able to get a better fit to your training data, which means you'll get lower perplexity on the training data, and maybe by extension on the test data. Back to this picture, what are we doing? When we make our model deeper, we're giving it more parameters. We're increasing the computational cost. We're probably going to get better fit to the training data, right? So that play, I'm going to use a deeper model. I'm going to give it more parameters. I'm going to make it more powerful. That's the red play. Typically, when you do that, you also need to increase the training data because now you've got more parameters to fit. It's exactly the same principle as when we were doing n-gram models before. OK, so here's, to my knowledge, the first neural language model. It came out in 2003. There are different ways people like to teach these things. Personally, my favorite way is to just lay out the expression for what it's calculating and make it very clear what the parameters are. So I've colored the parameters purple in the case of the embedding matrix and pink in the case of everything else. What you can see when you spell it out this way is that at the innermost layer, you've got something affine here. That's a linear function. You've got a tanh. There's your nonlinearity. You've got another affine function where you're multiplying the output of that previous layer by some weights, adding something else to it. That's an affine layer. There's a bias. And finally, the softmax is the nonlinearity. Do people know the softmax? The softmax was exactly that function we used back when we did multinomial logistic regression. It's the thing that takes a set of values and makes it sum to 1. Makes it positive first and then makes it sum to 1. I also give you in this equation the dimensionalities of each of the vectors and matrices, so you can get a sense of how the size of this model depends on the vocabulary size V, but you also have to pick 2 hidden dimensionalities, H and D. At the very bottom of this, we have the word embeddings, M. And what I want you to see is that this is still an n-gram model. And you can see that because you see that I'm trying to predict the next word after words H1 through N. And I'm summing up only over those most recent words. I don't look any farther back than then j equals 1 through n minus 1 words back. So this is, actually, is this a mistake? Am I finding a mistake after all these years? So j should be, oh, I just indexed it from 1 to n minus 1. Yeah, if I had another word here, let's say I had an h0, the equation would not depend. It wouldn't go any farther back than those n minus 1 previous words. So this is a feed-forward neural net that maps the n minus 1 history words to vectors and then passes them through how many layers? 2. There's one, and there's the second one. This is what the computation graph looks like. This big fat part here is where we're getting the one-hot, these are the one-hot representations of the history words going in. You multiply them by m, and you get hidden word vectors of, I want to say the dimensionality at this time was somewhere around 100. It might be on the next slide. Nowadays, it's probably an order of magnitude larger. But you've then got affine and nonlinear transformations a couple of times before you get at the end to a vector that's incidentally the same length as the one-hot vectors because it's got one dimension for every word in the vocabulary. And you interpret these as the probabilities of each of the next words. So there you go. That's the first neural language model. We're not close enough. There we go. You can think of it as being similar to the multinomial logistic regression model, except some things changed. All of your features depend on these word embeddings. And so they're all learned. Nobody's going to have to hand engineer or think very hard about how to represent those words. Everything is learned end to end. And then you sort of feed this output back into itself and create a second round of features after the tanh. The parameters are no longer linear weights on your features. They're the matrices and vectors that you're multiplying and adding in, and the embeddings themselves. The embeddings are probably the most important ones. But you can't assign any intuitive meaning to any single parameter like you could with multinomial logistic regression, where you could understand a weight as being kind of like a log odds operator. How many parameters does it have? Well, I'm multiplying it out for all the different matrices and vectors. They had a vocabulary size of about 18,000, pretty small by today's standards. D, the dimensionality of the word vectors, they tried 30 and 60. The hidden dimension, they tried 50 and 100. They were doing a 5-word history. And so altogether, if you add it all up, the total dimensionality of the model was 400 or 500 times the vocabulary size, which is far better than exponential in the vocabulary size. They also did some ablations where they forced one of the matrices to 0 and eliminated most of those parameters. And they did some things like averaging instead of concatenating, and these things worked. I don't remember, maybe a little less well, in some cases a little better. But so they were really kind of exploring a space of related neural networks with different levels of complexity, different levels of computation. Why did it work? Well, it basically, the way people talked about it back then was, no matter how good you were at designing features in a classic linear model like logistic regression, this was going to be able to do better because with multiple layers, you could combine whatever features you figured out were working. What they're maybe doing when they're learning is they're smoothly exploring a continuous, smooth space of features that are kind of conjunctive and detailed and rich. I think that there's more. I think that there's something else going on here where when you're tuning the representations of the words and the histories together, you're tuning them all to this task, but somehow you're sharing statistical strength among the words because all of the words live in the same space. Anyway, it did work better. It sort of spoke to the importance of word embeddings, and after this, there was increasing amounts of research on how to build good word embeddings. The good news about training, again, is that we can use the same principles. It's a probability model. You can use maximum likelihood. You can use backprop and SGD. I think at this point they were using more batch methods, but if we were going to reproduce this work today, we would use the standard ADAM kinds of things. There's a lot more details in some of the textbooks. Again, something has changed. The log likelihood function is not convex. So when you're evaluating this model, you're not just evaluating the model itself, you're also evaluating your algorithm for estimating it, because it matters how you initialize and how you repeatedly update the weights. The other thing to say about this model is that this was done at a time when we were still using we were still using CPUs to train neural nets. And calculating log likelihood and the gradient was pretty expensive. It took weeks to train this thing. It actually doesn't sound that bad now, does it? 3 weeks. I remember doing some experiments around this time that took 3 weeks. It pissed off the other students in the lab because it would, suck up all the computational resources. But it's all relative. At this time, this was not practical. People were not going to repeat these experiments very often. So the availability of compute has played a major role in what methods we use for these things, obviously. Okay, so there's some things about this model or the set of models we've looked at so far. One thing that's kind of interesting about this model is that you don't build in any information about how the most recent word is maybe more important than the ones that are farther back. Everything about the relative order of those words is learned. It's not inherently a sequence model at all. It's really just taking a set of vectors, and each of the positions has its own set of parameters that are going to learn in what way should I pay attention to this word. There are some new hyperparameters you have to think about. You not only have to think about how far back in the history you're going to look, the length of the n-gram, you also have to choose those two dimensionalities in the middle. And we saw that they did some experiments and they tried different values. You can't interpret the parameters. We said that already. The architecture, I don't know. Did you find this intuitive? I did not. In 2003, I don't know. Now maybe I've just gotten used to it. We spent a lot of years together, me and this model. I don't know. I think most people did not find it particularly intuitive. It's not like, oh, you can have an idea about language or notice something about the data and then go and change the architecture to be better, right? Like improving the inductive bias of this, it's not obvious how to hill climb in that space. But the model got a perplexity reduction and it got people interested and it kind of started work in this area. So here's our feed-forward net. It's a fat cat because it's expensive to feed it. More layers, not very easy to understand, like most cats. Okay, so feed-forward networks are fine if your input is bounded in size and you think of every position as sort of deserving its own features. But that's not the way most people think language works. There's nothing special about a word being exactly 4 positions back. We think that it's more about the syntactic positions of the words and the ways they relate grammatically. This method also doesn't scale well to longer sequences. Imagine that you were going to scale this up the way we do now, and you were going to train on really, really long histories. Like, what does it mean for a word to be at the position 974 positions before the word you're trying to predict? Even when you relativize it, it's just weird. It also doesn't capture, I think this is the more important point, the way that words tend to combine locally with their neighbors to form bigger meanings. This is an inherent property of language that we have compositionality. I think Leon talked about this a bit last night. And this was at the heart of NLP for a long time, was how do you model the compositionality of language? There were also counter arguments. There are things in language that are not compositional. For example, the word hot dog does not mean a dog that is hot. It has a totally different meaning. Right? And this happens all over the place in language. So the nuance to this is that there's compositionality, but then there's also places where there isn't. And you have to learn which is which. And anyway, this kind of model was never likely to pick up on that kind of stuff, I think. So what we're going to do is we're going to talk about a few families or styles of networks that reuse parameters to encode sequences of arbitrary length. And I think that was sort of the key shift that started making this feel much more like going beyond n-grams. And I'm not going to give these in exact historical order. I'm going to give them in an order that's, I think, a little easier to follow conceptually. But they draw from different traditions within machine learning. So one way to do this is to say, I am going to build essentially sliding window kinds of features. So if I look at the whole history for the word, going all the way back to the beginning, no matter how long the sequence is, and make no Markov assumption, I can stack together all of the vectors for all of the words in the history into a big matrix, call it x0. And then what we're going to do is we're going to iteratively, at every layer of the network, define a new matrix that is just a new representation of that history. And we're going to do that by applying a convolution function. So the convolution function will importantly be applied in such a way that it doesn't depend on how many of these vectors I have stacked together. I can apply this function no matter how long my sequence is. And so what it's going to do is it's going to give me a hidden state representation of every history word at each layer. So it's like, this is my first round. Now I'm going to apply a function, and I'm going to get a new representation of the whole history that has the same dimensionality. And then I'm going to do it again, and then I'm going to do it again. And each round I'm going to use different parameters. So this is how we go from the 0th round to the next round. And what you can see is that there's a bunch of matrices that I'm multiplying in. So there's my linear, and then F is something like a tanh that's nonlinear and not parameterized. The key thing in here is W, which is the width of a sliding window. So what we're doing is probably better to understand with a diagram. We have our embeddings. This is the first layer. We're going to look, the sliding window width is 3. And I'm going to apply some functions to the first 3 columns together. So I'm looking at kind of a chunk of 3 words. And that's going to give me a new representation of the first word. And then I slide one more step to the right. And I keep doing this. And I look at every sequence, and I get every embedding, every clump of W embeddings in the sequence. And I iteratively apply the same function to get updated representations. And notice that nothing here depends on the length of this sequence. There are some hyperparameters. I'm going to have to choose how many layers am I going to do this. At every layer, what is my nonlinearity? I have to choose how wide I'm going to be with my window at each layer. I have to choose the number of filters. There were 3 here that I'm going to use to create this representation. But basically, that's the way convnets work. And so I'm going to apply the convolution, repeated convolutions at every layer. There might be versions of this where you tie the parameters across layers. I can't remember which ones got used in language modeling. There's this last little bit at the end, because at the top, what you have is this matrix XD after D layers, which is, it's the same width as the collection of words that I had at the bottom. So I have to do something to collapse this down to a distribution over the next word. I need to get it down to a single vector. So for that, we use something called pooling. And again, you have a hyperparameter choice. You can take a max element-wise. You can take an average element-wise. And then finally, you're probably going to run it through a softmax to give you a distribution over the words. That's almost always the final step in language modeling, is softmax to give you distribution over the words. So that's the convnet. And the thing I want you to take away from this is not the colors or the convolution thing. This didn't really catch on. There were a few papers about it. I thought it was kind of cool. But there's one thing about it that I think is quite memorable and worth noting. If you consider the computations that are required for encoding the history of word at position t, and then you consider the computations that you have to do to compute the word at t+1, do you see anything? Let's go back to the picture. To get all of the representations up to this point in the history, I have to run the convolutions across the whole matrix, and then I have to do that at every layer. So I'm going to do this deeply. Then when I move to the next word, I tack on one more embedding here. What do you notice? I don't need to redo all the computations again. I did most of the work. I did t-1 over t% of the work. Almost everything gets reused. The amount of extra work I have to do with each new word is small and incremental compared to the work I did on a long history. That's nice. We like that. Let's keep that. That was not the case with any of the models before. Computational efficiency. I keep trying to do this. Okay, so a few historical notes. Where did ConvNets come from? They originated in computer vision. Similar ideas with different names emerged in speech recognition, which is also dealing with sequential data. The seminal papers on doing this were around the middle of the last decade. There was a nice text classification paper, which I think a lot of people found kind of surprising. And then in language modeling around 2017. People did different variations on this. You know, if you find these fascinating, I think it's interesting literature just to look at the variations. People used what are called dilated convolutional nets. You had, as you moved to deeper levels, you had longer steps. So you would skip over some of the words and sort of learn to use subsets of the information, effectively giving you longer windows. So you can take a look at literature on this. I think of ConvNets as you know, the big thing was the speed. They were fast. They scale nicely to longer sequences, deeper layers. You can parallelize a lot of the computation in a ConvNet. So cheetah, fast cats. These are the fastest cats. Questions? Okay, the next one was really an important one that did catch on quite a lot. And for some time, people felt like this was the answer to everything in NLP. A version of the recurrent neural net. So the recurrent neural net, and the idea is older. It made its way into language modeling around 2010. Again, we have no Markov assumption. The history for the word is all of the words up till now since the very beginning. All of those can get mapped into embeddings just like before. But what's different is, unlike the ConvNet, we're going to map the entire history into a fixed sized vector. And this was both, you know, shocking that this worked well and frustrating to many people. Because the sense that, you know, that you can use the same amount of information, the same size vector, no matter how long your history is, goes against a lot of people's intuitions about how language works. But here we are. The way it works is you're gonna maintain this intermediate state. We'll call it S. At the beginning, just set it to 0. Maybe there's an initial vector. You train parameters here, but simple enough. We'll start with 0. And what happens at each round is you take the next word. So we're at state I. We're at position I. You take the ith word, and you do an affine transformation of that word together with the previous round state. You pass that through a nonlinearity like a sigmoid, and you get the new state. And you can do this repeatedly on the entire history by taking the word embeddings. And when it's time to compute a distribution over the next word, you simply take the state, multiply by another matrix, do a softmax, and now you've got your distribution over the next word. These are called recurrent because there's a recurrence. Each state depends on the previous time step state as well as the current word. How deep is this network? One way to think about the depth of this network is how many rounds of the recurrence did you run before you got to making your prediction? And you added one for every position in the past. So the longer you run this network, the deeper it gets. That's one way to think about the depth. Here's the computation graph for one round. This is your single word at time step t-1 coming in. This is the state from the previous round. These guys go through an affine transformation. Then there's a sigmoid. And then we do this final kind of mapping back out, projection into the vocabulary, dimensionality, run it through a softmax, and you get a distribution over the next word. If you're going for another round of prediction, you take this hidden state and you pass it forward to the next round. If you unroll this across many rounds, you can see it's a very deep network. You're adding a layer with a sigmoid, an affine and a sigmoid at every word that you see. This is the simplest version of the recurrent neural net. People added a lot of different kinds of mechanisms inside this, most notably gating. to make it more powerful, to solve some of the problems that that this initial model doesn't work particularly well. Notably, it has a problem called vanishing gradients. What you're doing is you're multiplying together many, many, many times. And so what happens when you're trying to propagate error into the distant past is the gradients tend to get very small. And so you just sort of stop getting information passing back through. The model tends to forget too much. So people tried different things to make this work. Again, gating ends up being kind of a really nice tool. The most famous version of this model is called the LSTM, or long short-term memory model. That became extremely popular. Although there were variants like gated recurrent units, there were many others that use these same basic ideas to come up with alternate, slightly more interesting architectures. But they all had this kind of recurrent structure where you keep some notion of a state from time step to time step and pass it forward. The other thing people did was to stack the functions and make them deeper. So you can do all of this calculation, and then you can pass the outputs at each of these rounds or the hidden states at each of these rounds into another recurrent net and run another sequence on top of it. But these things worked really, really well. They really convinced a lot of people that neural networks had a future in NLP, that you could learn the features end to end. They didn't parallelize especially well, but we were still mostly not using GPUs at this point. This is like 10-ish years ago. But they really started working better than the other techniques that were popular in NLP. And for several years, this was like really the workhorse. And it was like every problem, somehow you were going to work in LSTMs to learn how to represent stuff, and then use those learned representations in one way or another to solve an NLP problem, whether it was translation or summarization or other things. So Tiger, pretty powerful, pretty strong approach. Had really long run before the transformer emerged. Questions about RNNs? Okay, so here's what we've seen. We've seen a progression from, sorry, I didn't see you.
Okay, so when we introduced different neural models, there were like two arguments why the next one is better than the previous one. One argument is more in the architecture. So, for example, we're adding a state that's remembering the previous stuff, the history. And the other argument is more computational, like this is easier to train, this is faster to train. Do you think, and the similar thing is when we introduced the transformer, you said you were not going to talk about it.
Tomorrow, yeah.
Yeah, but transformer is good because it parallelizes well.
Yep.
Do you think that it's more due to the computation than due to the other argument about the architecture? Because I've heard differing opinions that if we could make the RNNs go fast, let's say we have some alien technology, alien CPU, GPUs, whatever, that they would perform as well.
This is a very timely question because we have that alien technology now. People have developed alternatives to the RNN. They're called linear RNNs or state space models that can be parallelized and can be trained fast. So people are doing experiments like this right now. And I think it's complicated. The space is complicated. I will give you one recent result from my group where we did a controlled experiment with something called a hybrid model that mixes recurrent layers with attention layers. And we compared that to a purely attention-based transformer. And we kept everything else the same. This is a rare thing to do a very controlled experiment at an interesting scale. This was a 7B scale. And we found that there was some theory to suggest that this particular experiment would be interesting because you can show that a hybrid model can do things that neither a pure RNN nor a pure attention-based model can do. And we found that that model got very similar performance to the same transformer-based model with half the data. So what does that tell us? Well, it suggests that if you can get the model to the point where you can train it on interesting amounts of data at an interesting scale, then these architectural things do make a difference for scaling and for the kinds of capabilities a model can pick up with different amounts of data. So I don't know. The simple answer is I think it's both. I think these things all interact with each other. Being able to scale to lots of data, I think, why did the transformer run away and get so much better? Well, you could train it on way more data than you could train the RNN on, was part of the story. But there are differences in what these models can represent, and that was also part of the story. We conflated a lot of things when we made that leap. That's a great question. Okay, what else do I have? I'm not done. I will reiterate that while I was able to point to some reasons why we felt each of these was maybe getting closer to a good way to do language modeling, none of these was designed specifically for language modeling. They all were imports from other parts of machine learning, thinking about other kinds of data. And the people who adapted them for language modeling were very smart and I think had an appreciation for language. But here we're all letting somebody else, in this case, computer vision researchers, who are perfectly wonderful people. Some of my best friends are computer vision researchers, but do they really care about language the way I do? I think the transformer was really the first model that originated in the NLP community, and then NLP through the transformer ate everything else in AI, and that's kind of cool. When I teach the rest of this lecture, you can guess what kind of cat I use for the transformer. Anyway, but they're also getting more expensive. All of these things are getting increasingly computationally expensive, and the transformer is really the point where it depends on having access to significant hardware if you want to train the model. I want to make a pivot for the rest of the lecture away from conventional language modeling to talk about some sort of related problems that we call sequence to sequence. And I think these were very mainstream for a while, and they still pop up in some cases. But I think it's worth knowing about them just because they're so closely related to language modeling. They are the test bed in which the transformer emerged, but they're slightly different. And they add sort of the idea of you have an input that you're going to treat a little bit differently than just the sequence that I'm predicting. So sequence-to-sequence models are sometimes called encoder-decoder models. If we're going to use that term, then we would call all of what we've done up till now decoder only. Like the language model makes no distinction between the words that it reads as input and the words that it predicts. Everything could have been decoded. The model gives a joint distribution over everything, even the input. But here, what we're interested in is sort of separating out two random variables. One is X, the input, and the other is Y, which is a sequence we're going to generate as output. So it's not that different, but it's different enough that I think it deserves a little time. And the classic motivation for this is machine translation. So what I want to do is I want to translate text in one language into another. And this is where this kind of way of thinking evolved in machine translation. And we're going to focus on that as a use case. But again, you could plug in other problems here, image captioning, speech recognition, many others. I think machine translation is an easy starting point. But before we talk about a problem, we should talk about how we're going to evaluate it. Machine translation evaluation is a rich area of research. I'm not going to do it justice. I'm going to give you kind of the classic moment when it became identified as a research problem that you could automate, and leave it to others who are deeper experts than me to tell you more. But the intuition has always been kind of the same. If I do a good job at translating, then I've solved two problems at once. I've generated something that's fluent in the target language, but I've also remained faithful to the original meaning. And those two things are hard to satisfy at the same time. And that's why machine translation has been a long-standing problem. It was one of the first problems people looked at in NLP back in as early as the 50s. And for a long time, people would evaluate the quality of machine translation output by having humans judge the fluency and the faithfulness of the output to the original input. But that, having people finding bilingual people to judge the quality of your system, it takes time, it takes money. And so as machine translation was starting to become a hotter area of research and more people were working on it, there was interest in automatically scoring the outputs. And so the first of these, the seminal paper that did this, there were a few others around the time, but this one really took off. It was called the BLEU score. BLEU stands for Bilingual Evaluation Understudy, meaning it's an understudy to the human. It was a simple way to compare the output of a system to a human-generated reference. So basically, yeah, and it was even better if you had multiple references. So it kind of scaled nicely if you had multiple human translations of the same input. And it was very simple. It was basically taking different engrams across the two sequences and measuring precision. We've come a long way in the 24 years since the BLEU score came out. This one did win a Test of Time award. The local group here worked for a long time and gave a lot of really nice contributions in this space. I'm not going to do it justice. I'm just going to point out that this became a rich area of research, automatically evaluating the quality of machine translation. I like to point to the BLEU score because it's very annoying. Like, this doesn't feel like it should work. And I think today people would say it's probably not the best way to do machine translation evaluation. But at the time it was introduced, it was actually quite useful in discriminating between different models that worked pretty differently. And it drove the field forward quite a lot for a long time. Machine translation got better and better. It was a good enough proxy to give a signal. So I use it as a reminder that evaluations in this field are absolutely necessary, but you need to update them and you need to constantly evaluate how well they work. And you can only take them so seriously. They're really only a proxy. That's what the U is, understudy. Ideally, you should do human evaluations at least from time to time to make sure that you're actually getting real information. Anyway, this problem is old. It goes back even to the 1940s. So these are two information theory researchers. Warren Weaver's writing to Norbert Wiener. He said, one naturally wonders if the problem of translation could be conceivably treated as a problem in cryptography. When I look at an article in Russian, I say, this is really written in English, but it's been coded in some strange symbols. I will now proceed to decode. It's maybe an interesting view of Russians. It gets slightly worse too. So the model that kind of emerged from this, it's an elegant way to think about the problem, I think. It's called the noisy channel. And it's just sort of a high-level pattern. When I have two random variables, x and y, I imagine that the first thing that happened, and y is my desired output, x is my input. I imagine that things actually played out in reverse. What originally happened was some probabilistic model generated the sequence y, and then it went through a channel that somehow distorted it or changed it and gave me back this observed variable x. And so what I want to do is reason backwards about what y was given x. So y, in the crypto case, it's the plain text or the true message, the missing information. X is the ciphertext, the garbled message, what you can observe, the input. And what you're doing when you translate is you're decoding back. You're trying to find the y that's most likely given x. This is the conditional probability you're interested in. But what my model says is that what really happened was I generated y first, and then I generated x given y. So I'm going to use Bayes' rule to convert this conditional probability into something going the other way. And then you notice that p of x is not actually that important. I don't need to worry about this factor because it's constant with respect to y. It's just scaling the whole quantity. And so what I really need is just to think about maximizing this product of the channel model's score of the input given the output and the source model's score of the input. this should remind you of what we said way early on in the talk, that we care about two things. We care about faithfulness to the input. How likely is this input given this output is like a matching score. And we care about fluency, and this is your language model. For many years, this is how we thought about the problem of machine translation. We have the faithfulness score, that's the channel model. We have the fluency score, that's the language model. This is a very nice abstraction. We could spend a long lecture talking about how you build channel models, how you build source models, but the whole thing kind of got swept away. Oh, I want to make a point about data before I talk about that. So if you want to build this kind of model, if you want to build a model about the faithfulness between sentences in French and faithful translations of them into English, then you need a certain kind of data. You need sequences in the two languages that have the same meaning. And if you have enough of those, then you could build a conditional distribution of one sequence given the other. This was called the translation model. Again, it was usually conventionally combined with a language model that scored fluency. And so usually typically in this research, English was the target language. And that was fortuitous because English was pretty much always available in large quantities relative to other languages. So you would build your language model on English, and then you'd build somewhat counterintuitively your translation model, which modeled the transformation from English into the input language. And then you'd use those together with a decoder to translate. But the key thing to build that translation model was you needed parallel data. Any ideas on where we might find parallel data? Literature. If you can get around copyright. Yeah, the European Parliament generates a lot of this stuff. And there are a few others that generate multilingual data because they are legally required to do so. The Government of Canada, the parallel proceedings in English and French of the Canadian Parliament were one of the first big sources of data. And I think that's actually, there are stories about the team at IBM that built the first statistical translation models, like going up to Canada to make a deal with the publisher of those proceedings to get digital copies that they could then train on. This is before the web, right? This is like the early 90s. But there are a few others. I think Hong Kong. There are some news agencies that put things out in parallel. Incidentally, my own research started with this problem right when the web was pretty new. So like right around the year 2000, 1999, the web was getting bigger, and we had this hunch that there was a lot of parallel data on the web. And we were trying to figure out how to find it. How do you scrape the web and find all the parallel text? I think people still solve this problem. Anyway, so before we got to neural nets, there were a huge number of approaches based on formal automata, expert crafted rules. This was often linguistic theory-based ways of doing translation with rules. And then it all changed in the early 90s when people started using this noisy channel approach and using bitext to train translation models. Around the 90s, late 90s, there was an open source implementation of those models and automatic evaluation. And then it really started picking up. And there was a lot of innovation in how you could design models to do the translation task. And it started out kind of word by word, and you needed bigger chunks. You needed to break the input into phrases, and then there were lookup tables where you try to find statistically likely phrases and stitch them together. People use syntactic parse trees to model translation. There are some really nice overviews and textbooks written on this topic. People tried a lot of things. There was one period where there was like a debate. Is it going to be based on syntax, or is it going to be based on shallow phrases? They both lost. Everything lost to neural nets that go word by word. And this is kind of a fascinating history. The idea goes back to the 90s. And then, around 2014, there was a series of papers that basically pushed the recurrent neural net framework that we talked about a few minutes ago to be really good at machine translation. And here, It's a little confusing. The terminology changes. The neural MT systems are not working on a noisy channel assumption. They're just going directly from one sequence to the other. So they're building a translation model, but they're building it to go from the input to the output, exactly the way you would sort of assume you would want to go, not the reverse like the noisy channel. So this is basically what it looks like. I'm going to build a probability distribution over output sequences E, given an encoding of the input sequence F. But this is also kind of a language model. It's just a language model that conditions on this F encoding. It's like I'm going to use the encoding of F to somehow change my language model, and then I'm going to generate word by word the output sequence of English words, conditioned on that encoding. So this is not doing the noisy channel thing. The encoding of the source sentence is a deterministic function of the words in that sentence. You now have some tools from what we learned earlier today to think about how that might work. But the key thing is that that encoding is then just kind of kick things off for the generation of the English sequence word by word. So let's think about how this might work. Here we're going to switch and have a German input because I stole this slide from someone who was working with German. I hope that's actually German. You do lookups on each of the words in the input, and then you encode, and you could encode different ways, but a typical thing to do at this point in time was to run a recurrent neural network forward over the sequence and also a different one run backward, and then concatenate the representations of the states that you got from those two neural nets. So what you're doing is you're like contextualizing each word in the sequence by what came before and what after. So if there's a word that's ambiguous or its meaning depends on context, you now have a chance to learn how to color the meaning of that word and get a better representation based on what came before and after. And so you stack these guys together into a matrix that embeds the entire source sentence. Nowadays, of course, you're using a transformer, but this was that came later. The idea of encoding the sentence is a bit older. So then that's how you encode. And then what you have to do is you have to decode into French. I'm sorry, into English. And so you've got, at every step with your recurrent neural net, you've got two inputs. You've got the previous word, and you've got the context, which is some function of that encoding of the French sentence. And so you have to decide which information from that context am I going to use. So you're going to need some additional mechanisms here to help you process that French in a meaningful way such that you can feed it into your recurrent neural net. And notice you also have the state from the previous time step. So this is basically the same as the recurrent neural net language model. And the LSTM was very popular here. But the only thing we've added is this extra input of the encoding process through some mechanism to choose what's relevant to the context when I'm predicting this particular word. But basically, the beautiful thing here is that translation has become a kind of language modeling, and we can learn it end to end using the same log likelihood maximization principle that we've used everywhere else, and the same decomposition into word-by-word scores that we used for language modeling. And so that was quite a transformation. A lot of complexity in machine translation went away, and it turned into a game of scaling up neural nets to learn from machine translation scale data. There's one thing I want to point out that was kind of lost here that always bugged me about this approach to machine translation. When you built a machine translation model with the noisy channel, you had two sources of data to help you. One was the parallel text to learn the mapping between French and English, and the other was the text that went into the language model to help you get the fluency on the output side. When you build a translation system this way, you lose the second one. You never train on English alone. You only train on the bytext. And so it was always surprising to me that we could do well at machine translation without having a language model to help with the fluency. It was only, everything you learn about English fluency in this system is only learned from the English side of the bytext. And that was orders of magnitude less than what you could do for a language model. This was always surprising to me. And I think things have kind of come around full circle, because nowadays, my understanding is that some of the best translation performance comes out of language models that were trained on massive amounts of text in both languages. Kind of an interesting thing. I think people talk a lot about the algorithms and the architectures. The fundamental question to me is always, what data went in to train the system? And did you lose something? And this felt like a step backwards to me, because you lost that language model. I will say there was a little bit of work that tried to do a noisy channel approach with a neural model, but it didn't pick up. Okay, there's one last technical thing I want to mention. When you're decoding from a model like this, the first thing to try is greedy decoding, where you simply predict each word by taking the max of the softmax vector, the output of the softmax vector, look for the most likely word, predict it, feed it in, and move on to the next step. But there's a sense in which this kind of greedy local choice might not be the best thing. And so people wondered, for a long time, is there maybe a better way to choose an output? And maybe what we should do is search a little bit more. And so I want to show you Beam Search, which is we get till what time? 12:30, right? Yeah, okay. So I want to talk through Beam Search, just because this is a very elegant algorithm. It's been around for a very long time. It's often quite useful in understanding the larger distribution of what your model can do. It comes up in language modeling as well. But it was important to the success of these models that you not always just consider the greedy output sequence. So Beam Search gives you a knob to control how many hypotheses you're going to consider. That's K, so you have to choose that at the beginning. You also set a maximum length. And then you have a scoring function that basically is going to be, whenever I consider a possible next word, given a history up till this moment, I need a score. And that's going to be the log probability under your conditional language model, your translation model. So Beam Search is quite simple. You start out with a single prefix, which has like a go. This is like the stop symbol, but it's at the beginning. So it's the go symbol. And 0 is telling you that it's a length 0 sequence. There's no words yet. And I have a set of finished hypotheses, which starts out empty. And the subscript here is telling me what position in the sequence I'm in. So I have no finished hypotheses of length less than what I'm currently at, which is 0. And I'm going to step through and move left to right incrementally for time steps starting at 1 and going up to 1 less than my maximum length. Okay, so I start off with an empty set of hypotheses H. I have not built anything yet of length T. I copy over all the finished hypotheses from the previous round, and I set the beam at empty for this time step. And now I exhaustively consider, for everything that is in the beam from the previous round, and every word that could continue it, I'm going to score that. I'm going to add that score to its current score S, and I'm going to concatenate that possible word and put this in the hypothesis set. And now I'm basically going to pop off the best thing, the max scoring hypothesis, iteratively from H. So I take off the best thing. This is a score together with a new T-length completion. And then I'm going to check. If it doesn't end in a stop symbol, then add it to B. Add it to my current beam. If it does, then I'm going to, I'm missing a piece. If it does end in the stop symbol, then I'm going to add it to F. Sorry, this is the else. I'm going to add it to F. And if I have enough things in my complete hypothesis set, if I have more than K things, I'm done. I return the max scoring item or the full set of K items. But what this will do at this point is it will have given me K completed hypotheses. But what I'm really doing as I move through this algorithm is at every time step, I'm trying to find the K best hypotheses I could build given the work I did before. This is not an exact algorithm. It has no guarantee that it will give you the best hypothesis unless K goes to infinity. And it doesn't have any guarantee that it'll give you the K best hypotheses at any round. but it's at least making an attempt. It's sort of semi-greedy. It's like, what are the best things I could do given what I did in the previous round? There's really interesting work on beam search, both as a practical tool. There's variations on it. There's different things you can do. How long should you run it? How much patience should you have? Should you keep the hypotheses of different lengths that are complete in different places? There's lots of different cute variations that give you different results. But there's also theoretical work showing that that beam search actually is principled in that it's trying to maximize a criterion that's a little bit more nuanced than the likelihood of the sequence. There's a great paper called "If Beam Search is the Answer, What is the Question?" If you're into that kind of theoretical work. But this is just a really nice tool to know about if you are building a model where you want to make sequential predictions, but you're worried about being greedy with the prediction sequence. Notice that the runtime will depend heavily on the beam width k. It will also depend on the vocabulary size, because deep in this inner loop, you're looping over both the beam size and the whole vocabulary. Notice that if you set k equal to 1, you're doing greedy left to right decoding. So it's nice and it generalizes the obvious thing. And as you increase the beam size and the max length to infinity, you're basically moving closer and closer to doing a brute force exhaustive search, which you would never do, but it's good to know that in the limit, that's where you would head. There's also variations that add randomness. People do pruning. There's if you like algorithms, this is still a place where you can find algorithmic innovation from time to time. Okay, I want to close, I think this is getting close to the end, with a few words about data. A lot of the discussion today is about the scale of the data, and that's nothing new. Back when machine learning started making its way into NLP in the early 90s, around the same time as the original statistical models for translation and the noisy channel, people were saying more data is better. The best data is more data. And it's very hard to argue with that. But I think it's important to remember that though it's easier to get more data and the data gets more diverse, we know less about the data that we're working with. And so today's commercial models, we really have no idea. I mean, we have some idea what they're trained on, but they don't report. And in fact, they treat the companies building these often treat it as a trade secret what they trained on. And it's not just what they trained on, it's how did they weight it? How did they mix it? This came up in Leon Botou's talk last night as well. This is, I think, extremely important to the performance. I mean, I'm not going to say I think. I know it is extremely important to the performance of the model, how you balance the different sources of data. And it will have a big effect on what the model's good at and what it's less good at. Our team has done open language modeling, meaning that we also share the data sets. And so I just like to highlight this. The DOLMA data set, the series of data sets we labeled DOLMA is available for experiments and study. I think this is incredibly important work because the data sets have gotten too large for anybody to inspect. This is one of the big, sharpest criticisms from people who hate language models, that we don't know what's going into them. We need ways to study this. We need better science of the data. We need better ways to talk about the data going in because, it makes a huge difference. It's possible that we could train models as good as the ones today on a tiny fraction of the data if only we knew how to select it. That would be really cool. That would be a great result. So there are concerns. People talk about data quality. That itself is a political issue. What makes data high quality or low quality? Don't take that term at face value. You always have to dig deeper and say, what do you mean by quality? What are the criteria you're using to judge whether text is high quality or low quality? These days, we use classifiers that are trained on data at large scale. So even the notion of quality is sort of open to discussion and question. But this has effects on fairness, on privacy, on cultural biases. Models tend to learn biases from their data and then amplify and repeat them. There's a huge amount of work on this, on these issues. And I think, I'm not going to say that data is the only source of problems with language models, but I think it is the largest source of both problems and capabilities that models have. So if you want to do scientific work and you want to work in this field, there's lots of opportunities here. I think this is it. This is again my summary of how to understand the landscape as things change. How should you think about at least the base language model, the part where you pre-train for likelihood. These days, you know, we heard about this last night. When you shift to post-training, you change the criterion, you move to a more supervised kind of data, and things get different. It's still a language model. It's still predicting the next word, but it is kind of a different universe. But I think at the fundamental level, understanding how historically we've made these different plays, change the inductive bias of the model, increase its capacity in neural nets, make it deeper, make it bigger, give it more parameters. We still see this, right? We still see people scaling up the number of parameters and trying to scale up the data. I think this gives you a roadmap for what kinds of things are likely to come. That's it. The rest of the slide deck, which the instructors can share with you offline or put on the web, will give you all the references. And we have about 15 minutes for questions and chit-chatting and whatever else. I think I went faster this year. Usually we only have 10 minutes. You didn't ask enough questions.
How useful do you think the deep linguistic expertise is for current language models development?
Okay, I get this question a lot, and every time I try and think about how I can make the answer better than last time. So I'm doing a gradient update. So I think, you know, linguistics gives us a really, really nice vocabulary for vocabulary and language for talking about what's in the data and what kinds of things happen in the data. It doesn't give us everything, but it gives us a lot of abstractions and concepts that I think were very useful at many stages of NLP. And I suspect that they're still particularly useful for talking about the data. I said we have this massive data. We don't know how to study it. We don't have a good language for talking about it. It might be that linguistics could help. You know, one area I think is particularly important is sociolinguistics. And a lot of people have very simplistic ideas about language variation, right? Like, oh yeah, English. There's like British English and American English. And yeah, okay, but there's many of each of those, right? And there's a lot of variation within those speakers. And then there's many more that we don't talk about as much. And then there's a lot of people who speak English as a second language. Language variation is a very rich topic. And there are linguists who study it, and they have a way to talk about it. But most of that conversation doesn't make its way into talking about English variation in language model training data sets. I think that's an opportunity, right? That's one example. I think, you know, stepping back a little bit, I think you know, people talk about the bitter lesson, and there's sort of there's a bias against understanding your data. And I kind of disagree with the position that you're better off focusing just on scale and compute and never thinking about your data. I think a lot of the advances we've had in the field did come from having a respect for the data. And so is that necessarily linguistics? I don't think so. I think there are other ways to respect text data and language data that are not grounded in linguistics, but I think that is one of them. And so I tend to think it's worth knowing at least a little bit, and deep expertise might help out. But I have an addendum to this answer, which is one thing I've seen too much of in the field of NLP is people they overly identify with particular ways of doing things. Like, I'm a linguist. If I did my PhD in linguistics, I'm a linguist. And this is the mindset I'm in, and this is the way I'm always going to see the world. And I think that it's true. You know, if you do a PhD, it's a kind of brainwashing that puts a particular way of looking at the world into your head. It's unavoidable because you have to go deep on something, whether it's linguistics or something else. You're going to go deep into something, and that is going to inform the way you look at the world. But if you stop there and think, this defines me, and this is the way I'm going to do research, and these are the tools I'm going to use, and this is who I am, that's going to limit you because the field is going to change. And so I think, I work with some of my best friends are linguists. I had a linguistics professor who said once, some of my best wives are computer scientists. He happened to be married to a computer scientist. I actually have multiple friends who are linguists, and they've been delightful collaborations. But each of them, they didn't just view themselves as a linguist. It was like that was part of their training. That was one way they looked at the world, but they acquired more with time. And I think we all have to do that. No matter what your training is, you might be in a lab that's studying this topic or this problem. Trust me, it's going to change. It's all going to look completely different. If you're lucky, people will still remember the problems you worked on in your PhD 20 years later. I was feeling lucky last night because Leon mentioned grammar induction, which was a problem I did my PhD on. It's like, nobody talks about that anymore. I'm not teaching that at LXMLS. It's fine. It's fine. I moved on. I found other things. It didn't that problem wasn't my identity. And I think the same thing is very likely to happen to you. So I think you have to go deep, but it's all tentative. You're going to update your thinking. You're going to learn new things. So having deep linguistic expertise, use it when it's useful, but also learn new things. Expand it, because putting that together with something else is what's probably going to give you the breakthrough.
Thank you. I have a question about biases. So do you think that people try to fix, minimize bias by changing data, which it works, it makes it less biased. But do you think that it's a thing with probabilistic language models that by design, these models are always going to be biased more or less? So maybe it is a problem with treating models as language models as a model of language and not a model for a task. Because when you do one fits all thing, it's going to be biased in some areas, right?
Yeah, I think the idea of an unbiased model doesn't make sense.
Yes.
Right.
Yes.
It's an interesting idea. You're saying if we'd stopped trying to model the whole language and went back to just build a model that does this one thing, would bias still be a problem?
Yes.
And I suspect it probably would, for the same reason, right? It may be the case that you're introducing some biases by virtue of the fact that you're trying to model all of language, whatever that means, all the language in the data. It might be, but I don't think that is the entirety of the problem. I think
well, at least we'll use more specific metrics. So that's why for now, they use one metric and say, oh, it's unbiased, so it's good for everything, which is.
Yeah, I think we do. Look, it's always the case that the metrics that we're using to guide our research are incomplete.
Yeah.
And I don't think that's going to change. And that is a source of bias for sure.
Yeah.
Yeah. But I think that's true even when you move into a task. Right?
Mm.
I'll give you an example. One of my favorite problems now in my secret other life when I'm not doing language models is I'm really excited about music transcription.
Mm.
Okay. And music transcription is almost surely all biased by a number of facts. One, that we're using Western music notation, which is great for some kinds of music and not others. Two, the fact that we mostly train on piano because that's easiest to get data for and synthesize, and a bunch of other things. Chopin is overrepresented in the data because pianists love Chopin. Okay. Didn't do much for my instrument, but it's fine. So you're never going to get completely away from that because there is this long distribution, right?
So yeah, about distribution, do you think that there's a way to step down from probabilistic language models, and maybe there were some things with, for example, with oh, we should do maybe use category theory for modeling language or stuff like that. So stepping down from distributions.
It's very, okay. We talked about brainwashing in the PhD. Some brainwashing I have been very unable to undo is my appreciation for probability as a tool in learning. But I've also gained maturity, so I won't write it off and say that's crazy. I'll just say that's probably not going to happen in my group because I don't understand it. But good luck. I think it's good for, like, I want to encourage people to try diverse solutions. It sounds risky. You've got a big monster to fight, like winning over probability. You got to convince a lot of people. But I would like to keep an open mind, and maybe there are other ways to do it. Maybe, I don't know. We have this one paper. I think this is sort of related. It was an idea that didn't, like most of my papers, it didn't take off, but I thought it was quite compelling. And I still kind of believe in it. The idea, it was a little bit more about evaluation, but it was like saying, it was less about how to build the models and more how we evaluate. And the claim was, what we're usually doing is we're testing like an average performance. But what you kind of want is to test that the model is competent, that it actually solves the problem. And if you vary the test example in particular ways, the model would keep the right boundary and it would do the right thing. And so we built like collections of test examples that together you had to get all of them right to get the problem right. We called it competency problems. I think that was a little like, it wasn't an abysmal failure. It influenced some people's thinking, but it was. I think if we had tried to like completely radicalize the way we trained models to do that, it would have been much harder to get it published and to like influence people. So I think sometimes it's like, try to get to the core of the idea and find the minimal change you can make that might change the way people think, rather than overthrow something like probability, which has, I mean, like you're fighting with Shannon now, right?
Thank you so much.
Hi.
Hi.
Up here. Hi. So I work with sensitive data which can't leave the environment. So the models that we use have to run locally. And I work in health.
Yep.
Where no one wants to spend any money.
Thank you for keeping the data private.
Obviously, the temptation is to throw the more modern small language models at everything locally. And I think, and I include myself in this just about, but there's a generation of people coming through where NLP has been language models, that have been trained on billions of parameters without old rules-based NLP. And the answer for engineering scale is probably hybrid models, I think. And I suppose my question really is, are there domains that you think old rules-based NLP remains perfect for and was solved, or is there a constant gradient pretty much across all problems where you think that the more modern models are solving issues that were always there?
So I think the first thing I want to say is that I don't think it's like billion parameter, multi-billion parameter language models versus rules-based. There's a whole lot of stuff in the middle of that. We saw about a lot of it in this lecture, right? So we were data-driven for a long time before we were neural. And I think that there are, but I can point to examples of problems where I do think even rules-based is still the way to go. If you want to build a good, faithful model of the morphological processes in a complex language, you're going to use finite state transducers. You are not going to try to learn this from data. It's much, much more efficient to get it out of an expert's head and have them encode the rules and write the thing down. And you can add robustness later. There are a few problems where that holds. I think, when we get into more niche domains where you have more limited data or more constraints than what you do, I think thinking about hybrids where you have, more inductive bias is kind of my way of saying it. I think of it as a spectrum, right? The transformer is a pretty weak form of inductive bias. It's basically designed to scale for lots of data. But there are a lot of models, there are a lot of approaches in the middle where you can build more of what you know into the problem. And so you'll be able to get by with less data. The thing that's been hard to get away from is the value of pre-training, right? This was like Elmo and BERT, and then, it's people still, I think, use language model representations as a starting point. So pre-training at high expense, something very, very rich, and using that as a starting point seems just to be the best way of getting features for many, many, many problems. Obviously, if you're doing that on a set of languages and then you move to something completely different, it's not clear that much is going to transfer. But the thing about language is it's not like health language is entirely different from what you pre-trained on. So it's probably still valuable to carry it over. The transfer thing is important. But I generally tend to think that if you can customize a solution to a problem you can define clearly and you can evaluate well, you're probably better off doing that.
Thanks.
Thank you. I had a question, and this is a very general question, but so far among all the models that you talked about, as a post-hoc realization, we kind of see their architectural failures, right? But we have not seen something that obvious for transformers yet. There have been minor changes in the architecture, like rope embeddings or recent mixture of experts, etc. But as an architecture, we have not witnessed the scaling limit in terms of parameters, data, and so on. So do you think that something like that is likely to come up, or will there just be gradual changes to this silver bullet sort of an architecture that the field is dealing with right now?
I'm not sure I agree that there was a failure. I think with each of these, people kept working on it and changing it and modifying it and trying variations until something clearly better came along that was different. But the RNN didn't fail. It was just replaced by something that was better. And that's probably what will happen with the transformer.
And do you see any particular points of improvements that inherently arise from the mathematics of how, or the architecture of how transformers work, where this something better has an opportunity to come up?
Well, I mean,
for example, the forgetting part with RNN.
Yeah, I mean, I think right now I have a recency bias, but the thing that's salient to me is transformers are not great at state tracking. And so, we did experiments with hybrid models and we found that there's also theoretical results that a hybrid model can, by hybrid, I mean mixing linear RNN layers with transformer layers in the same model. There are theoretical results that can do things a transformer can't, and that an RNN can't. And now that we have variants of RNNs that parallelize, this is an architecture that seems to work. It so far seems to be giving better scaling properties than the transformer. I don't know if that's a quantum leap forward in the way that going from the RNN to the transformer was. I mean, the RNN to the transformer, there was a middle thing we didn't cover, which is people put attention onto RNNs, right? So the transformer, I think, when that paper came out, I didn't think it was all that radically. I didn't find it that surprising. It's a little surprising that you just got rid of the recurrence, but the fact that it can look so far back, I found it annoying because computationally it's got this quadratic thing. Sorry, I'm stealing Andre's lecture from tomorrow in a very roundabout way. But I don't think it was, I wouldn't say it's going to be oh, here's this fail. It's not like identifying a failure in one model immediately leads you to the next thing. It's not enough. People know there are problems with transformers. There are things we don't like about them. That doesn't immediately get you to the next solution, right?
Thank you.
No, dear.
Hi. So continuing off from this question and the slide behind you, let's say if you were a leader of a group of researchers and you're trying to focus on one of the or many of the directions behind you, what would be more interesting to you as a, let's say, the leader of this group of researchers to tackle? What would be interesting nowadays for you to see where you can gain the most improvement or find something interesting in which of those directions? If that's what are your interests and how do you see nowadays all those directions?
Yeah, I mean, I'm not a leader at Google. I'm a leader at a much smaller institute with orders of magnitude less people and resources. I tend to make the blue and green bets. I'm I also think, in particular, like, both pre-training, but also very much post-training, like the design of the data sets, new tools for synthesizing using language models. I think that is exciting because, it can help you customize the capabilities. I think I tend to think less personally about increasing model capacity and scaling up because I just can't afford it. And more to think about smarter architectures that are more modular. So like, how do you exploit the mixture of experts in a way that gets you better performance and less forgetting and things like that. So I think there's creative things to do in all of these. But I tend to, as a research manager, I like to keep a broad portfolio because you never know.
Like a smarter use of the current tools that we have to generate better data.
I think people pay less attention to data and evaluation than they should.
Interesting.
Yeah.
Thanks.
So eval is up here, right? Eval is that last link at the top. How do we measure better performance? I think this is just like, it needs constant new thinking because we always end up either realizing that the benchmark had flaws and it wasn't really measuring what we wanted, or we've overdone it on that benchmark and we've saturated it and we're not really getting more real performance gains by pushing on it.
Right. Okay, thanks.
So thanks for the interesting presentation. Maybe following up on evaluation, I care about reliability and uncertainty in, let's say, large language model outputs. And we've seen that these models are super capable, but they're also super complex, and we can't really cope how reliable or how confident answers are, especially now with more and more instruction-tuned models being put into use. These models are hyper confident, but outputs must not always be correct. So my question would be, so from prior work I've done, I've seen that lots of this is being done in post-training. So we take a look at logits, we take a look at stability matrices. But nowadays, Frontier Labs, for example, OpenAI, they're trying to shift this problem again back into training with your expertise also in training. How can we cope with, let's say, the evaluation of reliability or the confidence of a model to actually align with and or go back to where we actually are calibrated? So let's say a confident output is actually a right one over time. Is this tackled in post-processing, like the things I'm looking at, or does this need to be pivoted to training again?
I don't want people to stop studying this, but I'm not super optimistic about it. I think my sense is that this is a very hard thing to train for at any level. And the most practical way to think about it in the near term is to remember that the technology isn't just the technology, it's also the socio-technical choices we make around it. And so, this is like changing hats. I'm also a vice provost for AI. And part of what that means is like, how do I help my university community think about how to use AI and when to use it and when not to? And I kind of hate the idea that people have to adapt to the technology, but like, you actually do have to learn to use a new tool. And we're still learning how to use it. And a big part of knowing how to use it is like understanding what it is and what it is not, and not just taking its output at face value. I think we heard this yesterday. This is probably a recurring theme across the summer school. So I think a lot about like, how do I talk to people who don't understand how these things are built? They would glaze over by slide 3 of this lecture. How do we get them to the point where they are literate, competent users of the technology and somewhat inured to this overconfidence issue? I'm constantly thinking about new ways to do that, but I think it may be that the most practical way forward is not change the models. It may be help people understand how to use the models better.
Maybe a small follow-up, but don't we need somewhat the ability to pinpoint on how qualitative an answer is? If we as humans, we might be able to cope with that and we might be able to understand this, but if these models are being put into automation workflows in industry for, let's say, critical applications, don't we need some form of knowing how reliable an output is?
I'm not the one putting them there. I love your question, but I don't have an answer. That's not my job. My job is to prepare people like you to live in a world where these things have been done to us.
Thank you.
Yeah, thank you for the talk. I just had a question around, like, I think the field generally separates into like pre-training and post-training when you talk about like training language models. So do you think the separation is justified? And if so, where do you think people should focus more efforts in research?
I'm not going to tell you what to do. I will say we recently reorged my team at AI2, the team that builds Olmo, and we didn't do it around pre-training and post-training. We did it more around, you know, the work that has to go into scaling and different kinds of capabilities. And because I kind of think of like pre-training and post-training are choices that you have, and the boundary's not so clean, right? Like a lot of things that end up working in post-training, we kind of pull them back earlier and earlier into the process. Like put your SFT data into mid-training. That tends to be a good idea once you're pretty confident that you've got good data, right? So I would love it if we didn't have this complex curriculum. I would love it if it was simpler, but I also think that people shouldn't specialize too much too early. And so, you know, I kind of like having my pre-training people and my post-training people talking to each other. Some of the code bases are shared, right? There's a lot of things that are in common there. And I think the deeper philosophy, when you have a small team, one of the advantages of having everybody a little more connected is that ideas can spread better. But if you have a very large team, you know, it's probably as good a way as any to break people into smaller groups, which you kind of have to do if you want people to make progress. So I don't deeply object to it. It's not how I chose to organize my team for the time being. But I wouldn't recommend people it's kind of like linguistics. Like, don't be a linguist. Don't be a pre-training person. Don't be a mid-training person. Don't be an early mid-training person. Like, you see how ridiculous it gets after a while, right? Like, these are tools. Understand the tools. Think about problems you want to solve. Maybe it's very obviously something you need to solve at post-training for now. But like maybe later it won't be. I don't know. Thank you for the questions.